Dr. R.P. Singh has also created a number of kits, and please talk to him about the kits as well. He's open also to discuss what else could be done with the kits, etc. So do have that conversation. And just so you know, this is the first cohort of the Maharashtra government's quantum mission. Government has set up this training activity, but also government is going to give funding to set up labs.
Oh, great.
Fairly significant. So all of these so these are 4 institutes, 4 of the top institutes in Maharashtra represented here, and each of them will get the grant to set up labs.
Labs, 4 labs, yeah.
And the
Over
intention is that they also create access to the lab to local folks.
That's great, yeah.
Areas.
In fact, Gujarat government asked me to suggest setting up lab. Okay, why one lab? You should have at least 4 or 5 labs all over the state. Otherwise, some people will have advantage, some will have disadvantage. So that's what I suggested. I don't know whether they have taken a note of it. Okay.
Then over to you, Dr. R.P. Singh.
Okay, thank you very much for introduction and asking me to be here and interact with you, learn from you. All are learners. Okay, we all are learners. I am not expert. Like I am going to start with classical communication. I have never taught classical communication, to be very frank. You might be knowing better if you are from electronics and communication compared to me, because I have not taken lecture on classical communication. I go straight to quantum communication. So some basics of classical communication we will cover. Okay, and I came to know that Srirang has started like Shannon entropy, quantification of information, all those things he has already taught you. So let's go to, and what is the plan? Like I have to cover quantum 1, 2, 3, and it covers like basics of digital communication, Shannon entropy, and classical information quantification, and basic ideas of quantum communication. Next is like security of security involved in quantum communication, and then fiber terrestrial quantum communication and what are the current status. Last is free space quantum communication and what is the current status. That these are the 3 lectures I am supposed to cover. But what I will do, I will first talk like basics of digital communication, some Shannon entropy and other things. Then I will go to basics of quantum communication and free space and current status. I will be covering security attacks and all those things terrestrial like fiber based last lecture. So I have just reversed, and it's I think it should be fine, should not have problem in following. Okay. So that's what I have planned, 3 lectures. That why I should I must tell you why, because most of the time I talk free space quantum communication. I don't talk fiber based quantum communication. Being from Department of Space, our emphasis was on free space quantum communication. So most of the time I go around talk on free space quantum communication. So slides were already there, okay, for free space quantum communication. I prepared some slides for this classical and all those things. So that's why I am first going for free space, then I will be covering fiber based. I will prepare some slides. I have read, I know, but I will have to prepare the slides for that. Okay, it will take time. So that is the idea. So quantum communication, we will go later. That's the like subject. So these are the basic. First, let's go how this classical communication or traditional communication happens. You have source, okay. So source that may be analog signal or digital, anything it may be, okay. Then you do the source encoding, you digitize it basically, okay. You digitize it, then put a discrete mark, then above that you discretize, then you above some value you put 1 and 0. So that's how you digitize the source, whatever is coming in a log or whatever, and then you like discard the redundant bits. Okay, once you have discretized, and binarized, okay, digitized. Okay, what happened? So 0 1 and then some bits are redundant, you can discard them, okay, and then you send to the channel encoder. Okay. Lot of things happen here, okay, discarding. There are many algorithms used for discarding the redundant bits, like what it does, like suppose you have I have picked up example from internet only. Suppose you have glass vase, okay, and it's covered in a big box to make it safe, okay. Now you have to send over that channel and so that it reaches safely. So first source encoder what it will do, it will take out the vase, okay, and then it will pack in a very compact way, okay, so that all the big box is gone. Now it is very compact, okay, you make it compact, whatever space is required exactly that much it will use, so that it becomes compact box. And then channel encoder put like some wrapper, bubble paper and all those things, so it goes safely through the channel, okay. And then channel decoder what it does, it takes out the wrap and then source, it should be source encoder, source decoder. So then channel decoder takes out the wrap and then channel source decoder, like again you get the base, you remove that box and take the, so that is the idea, okay. And what Shannon did earlier, it was analog communication, all the signals were analog and all. In 1948 he wrote a paper, mathematical theory of communication, and there he told you can send this through bits information, that was the idea. So that is why Shannon give this theory, this bits, using bits you can send information, or okay. So that from there it started digital communication, earlier it was analog communication. I do not know why it is going again. Oh, no signal. So Shannon's contribution was that he told that you can send information using bits, okay, and that is the best way to do that. He told that through any channel, okay, and so that is the idea. You can send information through bits 0 and 1, that was introduced by Shannon. So all these channel, source encoder, channel encoder, channel, then it is a physical channel, it can be free space or optical fiber or any copper cable and all things. Then this is the idea. So you
last one should be destination decoder.
You can a destination decoder or source decoder. It is wrong written, it should be source decoder basically, it is wrongly, just copy paste while making the boxes, yeah. So then it reaches to destination your information whatever it is there, okay. Like again suppose you have digitized and you want to hear the voice, then again it has to be like analog, okay. So that is what you do. And one thing, when you are sending this, it should be clear, okay. So it goes over like optical, suppose optical fiber is there, it goes through electromagnetic waves, okay, and they are the continuous waves, okay. So here your information is digitized, but not the carrier. So how do you send this digitized information through carrier? You modulate it. So this channel encoder is having some modulator, some particular variable you select, okay, amplitude you modulate, okay. So you are encoding your digital information in the carrier, you are, that is what you are doing modeling. Or you can have phase, okay, phase thing or frequency. So you do the modulation of the carrier which is taking digitized information, it is digitized information in the physical variable associated with that carrier, okay. So you send this, everything is digitized, but carrier is, you can't just send 0 and 1, okay. Why you can't send 0 and 1? These will form a sharp square wave, okay, and for that you need infinite bandwidth, okay. So, that you can't do, that is a problem. Fourier, if you know this Fourier series and all. So, for square wave you need lot of like very high bandwidth. So, you will have to have very high bandwidth in fact. So, you can't send the 0 and square waves through the channel. So, you use carrier for this digital information, so that it goes to the particular place. Okay. So, you amplitude, phase or frequency whatever you modulate, and then again this channel decoder demodulates. Okay. So, these are the modulator demodulators. Okay. It is a kind of modulator and demodulator, and this is the carrier, over carrier you send, and then. So, framework is like digital communication, but carrier is like electromagnetic wave or anything like that. So, quantifying information, I think Srirang has covered. So, what is information theory? I told you this was Shannon, Claude Shannon. So, instead of measuring how important and meaningful a message information theory, quantify how much uncertainty it resolves. Okay. Like they give example, this is the example. If I tell you it is going to be sunny tomorrow in the Sahara, it does not make like convey you much of information, because Sahara desert it is always sunny, most of the time is sunny. But if it is going to snow in the Sahara desert tomorrow, that carries a lot of information. So, it resolves the uncertainty. Okay. There may be some possibility of having snow in Sahara, there may be some weather disturbances, but this resolves the uncertainty whether there is. So, that kind of thing it resolves uncertainty, unpredictability, okay, unpredictability, uncertainty, and that is a surprise element. Okay. So, that is what it does, this information quantification, this entropy and all those things information. Okay. And information and entropy are related, this average information is basically entropy. If you have a system and then you do the average information of that, that is the entropy, we will see. So, that is what the and the unit of measurement is bit. How it is bit, you can see that. Okay. So, 1 bit of information represents the amount of data needed to choose between two equally likely. So, two equally likely. So, 0 and 1, or you toss a coin. So, head and tail, they are two equally likely events. So, with that you can have only 1 bit of information. That kind of system like tossing a coin or off and on switch. So, you can have only 1 bit of information you can convey. So, that is the 1 bit of information, and this information entropy, because entropy is basically averaged information of the system. So, unit is bit only. Okay. Entropy is nothing but average information about the system. Okay. So, this paired coin if you toss, and that will have like 1 bit of information through that system, you can say bit is digital bits. So, 0 and 1 that kind of system, and this is the like mathematical formula. If x is the random variable and probability of getting this x is p x. So, it will convey this kind of information, single event. So, if you toss like and then you have suppose roll 8 sided die. Okay. So, this will have 3 bits of information, okay, 3 bits. Why? You can calculate that, means you have to make like you have to ask questions yes and no kind of thing 3 times, then only you will reach to that result that you have like got 5 on the rolling. Okay. So, that is the idea. This is all taken from me. I have not like taught this course. So, I was just going through and learning. So, as I told you already, this is information entropy is basically average of information is basically entropy of a system. So, suppose you have coin. So, here you have head and tail, there are 2 events possible. So, if you want to calculate entropy for this system, this binary system where head and tail, there are 2 possibilities, you have to have this Pxi, and this is the formula. So, I here head and tail 2 events only, you calculate that thing, and you can calculate, if you calculate this will be like 0.5 p p log pf, okay, p head log 2 p head, and then you do the minus 1 minus p, probability of getting a tail is 1 minus p. So, you do, it will come 1. Okay. So, that you calculated already information, but average if you calculate, then also it will be 1. So, 1 bit of information through that process you can say. So, high probability, low surprise, less information you have, that is the basically, and low probability means high surprise, that is what the Sahara desert example was there, and 1 bit resolving charge between 2 equal 50-50 possibilities. So, that is the 1 bit of information. Why does entropy matter for communication? Entropy sets the absolute physical limit for data compression. Okay? That is the idea. Then Shannon's source coding theorem, it is very important. You cannot compress a stream of data to a size smaller than this entropy without potentially losing vital information. Okay, that is the idea. You can't compress, suppose a stream of data, bits are there, you can't compress or any alphabet, suppose you are sending information through some symbols, okay, that may be 0, 1, other symbols. So, you can't compress more than that, what is the average information per bit. Okay. So, suppose like I gave example of this 8 sided dice. So, there it was 3 bit. Suppose you have some system or some message where per bit information is 2.5, there it was 3, okay, for any symbol to come 5, 6, 7, it was 8 sided. So, but here suppose this is 2.5 bits. So, you can't compress this message consisting of these symbols, so that this average entropy becomes 2 bits. It has to be this maximum, you can't compress it, otherwise you will lose information. So, you can't compress that message information such that this entropy reduces. So, that is the basic, and you can say what is the connection between this quantum communication and what do you start. So, this information, basic unit of information is bit, okay, and even this quantum information, when you say qubit information, like bit, a classical information is a special case of quantum information. Okay. When you measure, it is classical information only you get. You can have qubit, okay, it is quantum information, you can do the processing, but once you measure, you get the information in bits. Okay. That is the thing. So, that is the connection. You can send your information, okay, you can send your information using qubits, but when you measure, you get information in the bits. So, you are encoding your information in qubits, okay, whatever you want to send, that information is in bits. So, that bit information you are using to code using qubits, then you send it, when you measure you get information in bit. Okay. And there is one lower bound, it says a single isolated qubit, you can't have more than 1 bit of information. Same is like bit only, 0 and 1 system, you can't have more than 1 bit of information. So, if it is single isolated qubit, okay, you can't have more than 1 bit of information, that is the lower bound, and that like sets the connection between this classical bit and quantum bit. Okay. So, that is why one should know, that is the only connection between classical and quantum. Okay.
So, the notion of information remains the same because you are going to measure it in entropy.
Yeah, entropy will be here, but when you do the quantum thing, it is von Neumann entropy, okay, because you are sending information from one place to another in terms of quantum states, okay, because now it is quantum states. So, till you measure, it is like quantum information, you are sending quantum information using quantum states. So, it is quantum information, quantum system information. Information is in the quantum system, you are using quantum states. So, for that you use von Neumann entropy. Okay. Like it is very similar. So, instead of like Px you write rho, okay, trace of rho log rho, okay, that is the von Neumann entropy. So,
Because you said that
all these entropy is very similar, thermodynamic entropy you say, or Shannon entropy. Thermodynamic entropy you know, you must be teaching in the classes thermodynamic, or any like von Neumann entropy, they are very similar. Yeah.
so because you said that one single qubit you cannot have more than 1 bit of information.
Yeah.
So essentially
Isolate.
Yeah. So essentially the same lower limit that Shannon has given would
Yeah.
apply here as well.
Apply. Okay. But you might have heard super dense coding, using quantum mechanics you can send more information using. So, it is not single qubit isolated qubit, you use entanglement as resource. Okay. So, entanglement the moment say 2 qubits are entangled. Okay. So, it is not, that is the catch, you are manipulating 1 qubit for sending 2 bit of information, but entanglement as a resource we are using, which is like correlation between 2 qubits. So, that is slightly a misnomer. Okay. So, that is the thing. So, quantum communication we can discuss more here if you have some questions regarding this. I will also learn again, because I have to give now, I have started giving lectures on how to connect classical and quantum. So, if you have more question, I will go and look into that, and I will learn. So, you can ask questions here. Yeah. Please feel free to ask question. That is how we learn. Yeah.
Questions will come as we go on.
Okay. So, fine. So, please do not hesitate, keep on asking questions. So, that is the. So, when you say quantum communication, means you are communicating through quantum states. Okay. Quantum communication means instead of this classical system, like classical how you say, classical how you send information, electromagnetic wave carrier, okay, then you encode. So, here when we say quantum communication, instead of electromagnetic wave carrier which is carrying the information, we have photons, quantum entity, quantum system. Okay. So, we have photons. Okay. So, through photons we send information. So, that is how, and photon you write a state is associated with a photon. Okay. Each photon you write some state, okay, associated with it, and with that you send the information. So, that is the quantum communication. So, you are sending information using quantum states, okay, that is quantum communication, and since it is a quantum state, it follows the quantum mechanical principles. Okay. So, quantum communication is pretty broad, very. So, it is used, this principle quantum communication, even in quantum computing. You can say ki what you are talking quantum communication, how quantum computer. So, what happens, I say you are sending information, okay, using quantum state from one place to another. In quantum computing what you do, there is quantum network. So, from one node you are sending information to another node, another node. So, you are sending again quantum information, okay, through quantum states, that is quantum communication. So, you have quantum network in the quantum computing also. Okay. So, and this sensing also, suppose you have quantum radar, okay, you want to have. So, you are sending quantum state to a far off place, and then you sense it, okay, using quantum states, okay. Or you sense anything, you send and probe that, okay, anything it can be. So, even in sensing and all those things, you have ideas of quantum communication. So, quantum communication is very broad. Whenever you are using quantum state, you are sending in quantum state, and how this state is changing, you can extract information. Okay. So, that is sensing basically. So, quantum communication is very broad area, that is what one should be clear. whenever you are using a quantum state to send information from one place to another, it may be very short distance, it may be long distance, okay, it is quantum communication. But till now, like quantum computing you might have heard, there are many platforms, okay, quantum computing, okay. I think you have been taught about quantum computing little bit. So, you have ions, neutral atoms, you have superconducting qubits, you have electron spin, there are so many, okay, platforms one can use for quantum computing. But in quantum communication, we are lucky that it is only photons, okay. There is no dispute about it, okay. Information has to be sent through the photons. So, it is photonic based. Quantum computing have photonic also, okay, we will go. So, you can have photonic quantum computing also based on photon, because quantum state you can make using photons. So, and then you can process the information so you can have photonic quantum computing and many other platforms. So, but when it comes to communication, quantum communication, it has to be through photons only, that should be clear, there is no doubt about it. And in quantum communication, like quantum computing, we have still noisy intermediate scale quantum computing, we can't do much useful work, okay, much useful information like which can be used in day to day life, still we can't do using quantum computing, that kind of thing, because it is the noisy intermediate scale quantum computer, a lot of noise is there, lot of error. Same way in quantum communication also, we are still very at the initial stage, okay, very initial stage. We just see the its use in secure quantum communication, that is the only use till now we see, okay. Secure quantum communication using quantum key distribution, okay. So, why can't you send just like communicate directly through quantum instead of making keys? So, that is a direct secure quantum communication, okay. But till now it has not been done, okay. There are theoretical protocols for direct secure quantum communication, where you instead of keys, quantum key distribution, what is quantum key distribution by the way? You make keys, okay, you make keys and distribute it using, and this making and distribution of key, making of key and distribution of key, if you are doing through quantum state or quantum mechanical principles, that is quantum key distribution, generating the key and distributing if it follows the quantum mechanical process, you have quantum key distribution. And why you are making key, anyway we will go and see why you are making key and what is the importance of key, and we will go these things, these terms and all gradually.
Secure communication is still not in practical.
Not in practical. Why? We will discuss that also, why it is not practical till now, what are the problems there, okay. You will realize why so difficult, okay. So, then some of the principles, like these are the quantum mechanical principles, no cloning theorem, uncertainty principle, entanglement, these are used for secure quantum communication, okay. So, as I told, our quantum communication is still limited to secure quantum communication using quantum key distribution. Still we do not have like quantum large quantum network, okay. We have network, China is setting up network, but quantum communication network, but we will see what is the problem with that network, whether that is really secure or not.
Network means the network like LAN.
Pardon?
As you said, China is creating the network. So by
China is like leader in quantum communication.
by network you mean LAN type of network.
Not land, they have like satellite also, satellite and land.
Complete
They are combining, yeah, full, yeah,
Only
full
one
thing.
or two channels are not there.
Yeah, many. It's a network. Yeah,
With
Many to many
outtakes, FSO, everything.
yeah. we will see. And what is the like why you are saying in secure quantum communication we are like still very primitive stage in quantum communication, we can use for secure quantum. Why we have embarked on secure quantum communication first when we talk of quantum communication? Why we have given it first priority? Let us do quantum communication first, we have to do secure our communication using quantum mechanical, because this quantum computers, once you have full fledged quantum computer is there, that can break present day encryption scheme very easily. Okay? That will become redundant. The present day encryption whatever we use, RSA or other Diffie-Hellman, all those encryption schemes will become redundant. Quantum computer can break those encryption schemes, and so you have to go for secure quantum communication, because if you are securing your communication using quantum mechanical principles, even quantum computer cannot break it. Okay? If you are securing quantum communication using quantum mechanical, even quantum computer cannot break it. Why the quantum computer can break the present encryption, you may ask? Because quantum computer has enormous quantum computing power. Okay? Quantum computer provides you enormous computing power, and they are very smart algorithms which can be implemented on a quantum computer, quantum algorithms. Okay? Some algorithms which can be implemented quantum computer, and with enormous computing power you can break the present encryption scheme. So, that is the threat. Okay? Quantum computers, if they are there, they can break the present encryption scheme. So, one has to go for secure quantum communication. That is why this has got the top priority, and commercial systems are also available now, okay, for secure quantum communication. There are companies which are providing commercial quantum key distribution system for secure communication. And then information leakage, what is the difference between this classical and quantum thing? Anyway, I will be distributing these slides, so just you can keep on, no need to waste your like storage because it gets full, then message will come, you delete delete your storage or remove create storage, WhatsApp will not work. So you have to remove then. So information leakage or error rate is measurable in
One question.
yeah.
Like, for example, if the current quantum computers, if they are there, can they now break the?
Right now there is at least nobody has informed that there is no result that it has broken. Okay, because you require very a large quantum computer, and that also fault tolerant, then only you can break. Okay, otherwise you can't break right now. But they are saying it is not very far, 32, 35 sometime. There will be computers, quantum computers, which will be able to do that, break that encryption scheme, because they are working very hard on fault tolerant quantum computing. They are improving. Like earlier, suppose you have 1000 qubit. Suppose you have developed one processor you developed where you can have 1000 qubit, you can process information contained in 1000 qubits. But that was physical qubit, but the computation like logical qubit, like you will get correct result, okay, after the operation, that was equivalent to only few qubits, okay, like 10 qubit or even less, okay, out of 1000 qubit, suppose physical qubit to do the operation, and which you can do with good logical qubit which are fault tolerant, hardly 10 or less. But they are reducing the gap now. Now it is like 100. Then they are going to have like, so
Then they will be able to.
yeah, then they will be able to. So there are lot of work going on in reducing the error in quantum bit like quantum information processing.
So, what is the minimum number of logical qubits before the current financial RSA like algorithms will be broken?
They are
How
saying
will-
ki if you have like 1000, now they have reached up to 1000 logical qubits, suppose you have fault tolerant, you can break now. So that is why they are saying it is not very far when you can break, that is the present.
So, if you have 1000, you can break the current RSA.
Mm-hmm.
But why can't you just go to a even larger prime number so that 1000 can't break, but you need maybe 100,000 and buy some more time?
So that will be
Race is on.
just race, that is a matter of time, that is all. But you can break. Yeah.
But perhaps
Like present, the kind of numbers they use present, that can be broken. Or suppose somebody is storing, I have some, what is the, like I will, so here let me go, this is very important. So somebody present the encryption scheme I am using and then I am storing information. I can always, there is in classical communication you can always tap without knowing anybody, you can tap the line and you can keep on storing the information, because you keep on amplifying the signal, booster you use. Okay. So nobody knows you are just storing the information. Okay. And it is using present encryption, like you are saying smaller, suppose prime numbers, because processing will take time. So smaller numbers. So it is using number 1 keeps on storing, the moment it gets 1000 qubit fault tolerant quantum computer, that will break. You may increase later, but all your information which was there stored by this person, okay, by this country, that will be known to person.
Sir, but what they are doing right now is for every session they have a separate key. So the public key cryptography they use only to encrypt the symmetric key.
Mhm.
And for every session the key changes. That's
Mhm.
why the session is not on more than 2 minutes or 3 minutes.
Mhm.
So next time I try to do, someone might know my symmetric key in this communication, but may not be in the next communication.
Gradually you can have, like suppose 2-3 minute communication or 5 minutes communication you can break, then again 5 minutes, it will take time, but it will, in principle you can start breaking that.
Yeah, and second point, Kunj sir, maybe I am just guessing that if you increase the size of the key, that's what essentially you are saying. In that case, the time that is required to encrypt and decrypt the symmetric key itself, which is there in the SS algorithm, that will also increase.
Time will increase, that is all. Suppose with 1000 qubit present day, if you increase the number, time will increase, that is all. So that is what I was telling, information leakage rate measurable. In quantum key distribution or secure communication, you can set a limit. This is the error threshold. If you are getting error beyond that, means there is some problem, it is no more secure. So that is the advantage you get when you are doing with secure quantum communication. You can put a threshold on error. Here in classical, there is no this kind of concept, there is error threshold. So anyway, you know that which are the customers for this secure communication. You have defense, health sector, bank and financial institutions, and critical infrastructure also, power grid, okay, command infrastructure, ISRO, rocket launch and all those things, they are also required, data servers, okay, access of data, whether it is secure or not. So all these are customers, okay. Telecom, I have not written telecom, telecommunication, all these are customers. So already what are the quantum mechanical principles which use? No cloning, entanglement, superposition, all those things are used when you. So I think this thing has been covered. What is I think you must heard these things. What is superposition? What is entanglement? And all those things you must have heard. I will not go into that, or I should repeat it or discuss on this slide. You can ask on this slide something. you have already studied, you have doubts, you have questions on this slide, you can ask instead of me repeating the slides. You have doubts on superposition or entanglement, you can ask, so we can, I can go ahead. You have heard enough of the superposition and entanglement, I think. Okay, I can go ahead. But I think you may not have heard this no cloning, because no cloning is very important principle in secure communication. Okay, because an arbitrary quantum state we are using for communication, you are sending information, even key information. So, it cannot be copied. Okay, it cannot be copied, nobody can clone it without disturbing. Okay. So, that is the no cloning, that is why this you have secure quantum communication or secure quantum key distribution. So, what is cloning machine or no cloning theorem? It says, suppose you want to copy or Xerox this quantum state and then some blank state you put where you want to copy. So, you get these things, that is a copier basically. Okay. Copying machine, that is what it does. You put a written page, put a blank page there, and it gives you the original and copy. So, just written in the form of state, quantum state. So, this is the cloning machine you are representing by U. So, you have these two things and you get A, that is the operation that defines the cloning. Now, suppose if this is your state is A plus B, okay. This is again a quantum state, get A plus get B. This is a superposition state of two states, and then you want to copy this state. Ideally, what you should get? Copy, this is one state, okay. This is one state, okay. So, you should get this, but what you get? You get this, which is not the same thing, okay. By you follow this principle and then you operate U on this, you get A, U on this, you get. So, you do not get this state. So, that is what you wanted to have when you are making copying this state. So, in quantum mechanics, this is one state, okay, superposition state, okay, one state instead of just. We should get this one, copy of this state, okay. So, this is one state, we have to get copy of that, but what we are getting here? This. U is this operation, what this machine is doing, we are representing by U, okay. That is what we are defining, this, that is what is doing copying, okay. We are representing machine by U. We have these two states here, and what machine does? It makes a copy of that. This is blank paper, blank state, 0 vacuum state, then you make a copy on that blank state. So, this is no cloning, superposition, entanglement, all those principles are involved, and somebody was talking like he was talking about this symmetric, asymmetric key and all. So, before we go for this quantum key distribution and or quantum cryptography, quantum key distribution is basically quantum cryptography. You are using quantum mechanical principles for cryptography, and cryptography, what is cryptography? You are sending some text and you do in such a, you encrypt in such a way, so that it is going, but nobody can read it, okay. So, hiding in plain sight, that is cryptography. So, you have a symmetric key and asymmetric key you can use. Symmetric key, what is the meaning of symmetric key and asymmetric key? Symmetric key, you have same key, okay. Both the parties which want to do secure communication, they have the same key. This is the plain text, then you encrypt it called ciphertext, and then you decrypt it, again you get the plain text when you decrypt the ciphertext. So, both parties use the same key, okay. Both the encryption and decryption keys are same. Example, encryption here by this is the key, and decryption, again you get the this. You encrypt this using key, and then you do the same key you apply, you get the, you apply on this thing, y is this, you apply, you get x. Then you have asymmetric key distribution. So, here keys are different both the parties. Uh, encryption and decryption keys are different, and this is the RSA famous RSA algorithm, which is like asymmetric, okay, based on prime factorization. So, both are not equal, these factors. So, one is here, one is there, okay.
This decryption key is some function of encryption.
Yeah, some algorithm, based on some algorithm they are related, then only you can decrypt, but they are different, okay. So, that is asymmetric, but in quantum key distribution, okay, we have symmetric key distribution. We have till date whatever quantum key distribution schemes are there, they are symmetric key distribution. We have same key, okay. How I am doing with time? Okay. So, this is one time pad, okay. One time pad that was again Shannon proved information theoretic security for one time pad. OTP is one time pad, means you use only one time, okay. This key you are using only one time, okay, and here one time pad is like you are using only one time, that is the meaning, and this key size should be same as message and then encrypted message. So, this is secure, okay, information theoretically secure, okay. If you are using your key, okay, which is of the same size as message and you are using only one time this thing, this key, you are secure, there is no point. So, but you have to have such a long key first. Suppose you want to implement, suppose message is very long, you have file of like 2 GB, suppose you have image, you want to encrypt it. So, your key size should be 2 GB, okay, and then you have to use only one. So, that is the problem. So, but for smaller like messages you can use, and that is what this OTP, you say OTP is coming. So, some code word, some login password, smaller passwords you can do that, okay, that is, and you are using once, so it will be secure. So, this is one time, and this is randomness is very important, okay. Again this quantum mechanical principles come in generating random number and kept a secret, never reused as long as the plain text. These are the
Last one,
yeah.
key distribution problem.
So, distribution it has to be secret, you have to believe when you are sending this distributing. So, nobody is having information about the key. Suppose somebody leaks or you are sending through wire, somebody taps and get that information, okay, because classical communication you know anybody can tap. So, these are the problems, how to distribute it securely.
Sir, are the both encryption and decryption keys generated at the end?
Yeah.
So how do we ensure that the random key is same at the both ends?
So, that is ensured, they do the comparison whether they are same, okay, or some process that can verify they are same. Yeah. You have to use some algorithm to check whether they are same.
States are entered, they both measure the thing, and if they start getting different results, then it is being.
There are many other ways, you can, there are protocols you can verify whether they are same or not, okay. You have to use algorithm to make them same, okay.
The last comment there is as long as the plain text,
As long as the message.
the current algorithms, do we actually use the one-time pad as long as the plain text, or do we use smaller ones now?
Right now, it is not like for very large message I told. So, even image if you see, not plain text suppose it is few bits, okay, you can do that, but suppose it is image,
Yes.
you have then you can't do that, okay.
So what do we do?
We do the AES thing. So, what you do AES advanced encryption scheme, you use 128 or 256 bits of key to encode that, to encrypt that information. Even 10 GB of file you can encrypt using 256 bits. So, still in quantum communication, quantum key distribution, if you are using commercially for securing the communication, so you are using finally you are using 256 of bits of key generated through quantum mechanical principles to encrypt 10 GB of file. So, basically keys are being generated and distributed by quantum mechanical principles, but for sending this classical information, as I told, classical information is the main thing. So, for sending the classical information, securing the classical information, you are using 256 bits only. So, it is AES, that is what they use, okay, till date. Till date you have like you can generate at very high rate this quantum keys, okay. Like you can use one time pad kind of thing. Suppose you are generating you are sending very large files and you are generating keys also at very high rate, then you can do those things. Till date it is not there. So, you are using AES keys, you are using that 256 bits key that you are getting from quantum mechanical principles, and we are using to principles AES we are using to algorithm follow to encrypt the files. So, that is what is happening.
So, communication is classical only, but keys are quantum.
Keys are quantum, right, yeah. Communication is classical, keys are
In
quantum.
this case, the random key, again coming back to question madam, the random key has to be known to the decrypting side beforehand, right?
This key should be, it is a key, yeah.
So, I think it gets transported to the decoding side to another channel, not to the same channel.
Yeah, you can use another channel, there are same channel, whatever.
But another way of
Another way, huh? You have to distribute key in advance,
right.
yeah. Then only you can.
So but that is the only random key. What if that gets
No, but but next time you are going to generate another one. So it is only for this communication.
when you are saying that it is getting transmitted through some other channel, you also have to ensure that that channel is
Yeah, so that is secured by using another way.
so that is
So yeah,
So, that is why the best way instead of transporting, what I say, instead of transporting, you generate there itself,
but
okay.
when you generate there itself, how do you make sure that both the keys are same?
So, that is the you do the error correction, you take a chunk of those bits, then compare whether there is any error, there are error correction protocols, you do the error correction, okay. And for error correction you have taken some bits to compare, okay. So, you have already announced what are the bits you are checking for comparison. So, you discard that. So, there protocol like privacy amplification. So, you discard that, then after that you get very small bits, okay, as key, and now they are same. So, you do the error correction, then privacy amplification, and then whatever key is it is same both the places. So, you do the comparison and then you do the error correction, so that it becomes same.
There is a specific hardware.
Pardon?
The specific hardware used for generating random keys.
There are hardwares, yeah, there are hardwares. So, random number generation again is full technology, you can use many process for random number generation. So, TRNG, true random number generator, quantum random number generator, then pseudo random number generator. So, most of the time people use pseudo random number generators. Pseudo random number generator based on again some algorithm, okay, you can generate. Then you can do like statistical test you can run whether they are really random or not. Random means probability of uniform, probability is distributed uniformly. Suppose 0 and 1 bits, bit in bit suppose you are making. So, probability of getting 0 and 1 is equal, okay. So, you and there are many other like tests you do on statistical tests to verify whether they are random or not, okay. So, you can use algorithm to generate these random numbers, that is pseudo random number. You take small seed of random number, again you say here you are getting small seeds of random number 5, 6, Okay, that you can run a test. Okay, you can write some numbers and then you run a test whether they are random, then you expand on that. So, that is a pseudo random number generator, and then you have true random, their process which are very random, okay, which are random process, like tossing of coin, that is random if it is fair coin, okay, very good. So, it is random. So, you can generate using those process, that is true random number generator. And then quantum random number generator, quantum mechanical process itself is like random, okay, it's inbuilt, okay. So, you generate using quantum mechanical process is a random number generator, and what is the beauty of this QRNG, you can verify that it is a quantum mechanical process, okay, and because it is quantum mechanical process it is random, okay. So, but here other two TRNG general, you do not have any certification, okay, you have just verification using a statistical suit, okay. You can't certify that process is random, the process is random, there is no certification for that. I assume that this process is random, but there is no certification. Here in QRNG you have certification that this process is random, whatever I have used. So, I am talking of this quantum key distribution, that is the most common, like ubiquitous visible application of quantum communication, this quantum key distribution we have already discussed. So, it can be discrete variable and continuous variable. You may say ki, what is discrete variable and continuous variable. I think you must have been taught quantum mechanics basic, okay. So, if it is like field quadratures you are dealing, position, momentum, that kind of thing you are dealing, that is the continuous variable. And if we are dealing with like polarization or time information or frequency, those kind of things are discrete variable, okay. And in both sides you have this prepare and measure and entanglement based protocols, okay, and there are number of protocols, okay, for that. So, once like prepare and measure, you prepare and send the state, this they based on measurement they get the key, and then prepare, you know how you are preparing the state, then they compare and get the same key. And entanglement based, you have entangled systems, you distribute entanglement measure, there are two parties, okay. So, you distribute them and then make measurements and then you get the key. So, in continuous variable entanglement, this is squeeze state you use, okay, and prepare and measure you use weak coherent states, and prepare and measure here also you can use weak coherent states, yeah, both sides. And then entanglements, here you use squeeze states, here we use entangled photons, okay. We will discuss BB84 more detail, yeah. Pardon?
GM based and BM based.
These are Gaussian modulation and discrete modulation. So, these are the Gaussian modulation, you do the Gaussian modulation, okay. And then like Gaussian, like it is a large random number, random process. If you do the distribution, it is Gaussian, very large number of events which are distributed randomly, you do the plot the distribution of that, it is Gaussian. So, basically it is a random kind of modulation which follows the Gaussian distribution. So, this is Gaussian modulation, this is discrete, okay. And then again you have quantum phase shift, yeah, phase shift keying and amplitude modulation based on amplitude. Then you have GG, this is again scientist name GG, Grenier, and I am forgetting the name, Grossman and Grenier, something like came in 2002, that is why it is changed.
I have one query. Right now we are using a classical communication, and future is about quantum communication.
Right.
And the danger is that in future this quantum communication may decrypt the information of all
Quantum computer, yeah, may decrypt.
classical. So is it possible to make secure this one classical information with respect to the upcoming danger of quantum
Yeah,
computation.
and that's what they are saying. You have to start using secure communication, quantum communication right now, okay, so that you can avoid that danger. So they are saying it should, you should start implementing quantum key distribution right now, so that from now onwards your information remains secure against quantum computer. So that is the idea. So quantum security should be the first, like it should start right now,
Already right now.
right now without delay, as early as possible you can do, so that your communication remains secure.
On the previous slide, you had two examples, the continuous and the discrete variables. Can you give again the examples that you took for continuous variable and discrete variable?
Continuous variable, again you use field quadratures measurement, you measure field quadratures in quantum. When you say this continuous variable, you define the quadrature in terms of quadratures you write, like electromagnetic field, okay, we are taking a light only here, here we are taking photon, here we are taking electromagnetic field, okay, and then we write in terms of the quadratures, okay, and then like amplitude and phase, that might be one of the quadrature components. Position momentum, again you can say quadrature component. So then you prepare the weak coherent state, and then using homodyne detectors. Detectors are different both sides. Here you have single photon detectors, here you have homodyne detectors, homodyne and heterodyne detectors. So you measure these field quadratures, okay. That is what you do based on measurement of field quadratures, or okay, you derive the key. Again entanglement also you are measuring field quadratures only, how they are correlated, okay. So based on that field quadrature measurements, that is through homodyne detection, heterodyne detection, homodyne detectors, heterodyne detectors, you get that information, and based on those field quadrature measurements you get the key, okay. But here you measure the photons, okay. So you use single photon detectors, here you use homodyne detectors. I think I had one slide, I did not put okay, much more detail, some other talk it might be there. So but that is the idea, detection scheme is different in both, okay. And some people argue that this is better way to go, continuous variable quantum key distribution, because this can be like this homodyne detection, it is based on interference. So you cut out the noise, okay. Suppose you are doing daytime, there is so much of background signal, but because homodyne detection is based on the interference, so interference only the reference and the signal will interfere, rest is cut down, interference it will not happen with a background, okay. So this homodyne you can do even in daylight very easily, okay, and then homodyne detectors are less expensive, much cheaper, their efficiency is very high, okay, compared to single photon detectors. So they are saying it is much better way, but for long distance still security is not proven for this continuous variable, that is the only thing, okay.
Long means how?
Like if you want to go beyond 10 to 15 kilometers, is still not proven, okay. So that is the problem. Otherwise it is being tried out. We have done this continuous variable quantum key distribution also in our lab, okay. We took it to the field, in field we could not demonstrate that, there was problem, okay, but we are trying at PRL, yeah, to have field based continuous variable quantum key distribution. But lab we have published, okay, we have results, lab based continuous variable quantum key distribution, we have published that, okay, 2-3 papers are there. Most of the time I will because when we say discrete variable is more intuitive, okay, to follow. When you say quantum discrete thing, you always associate quantum thing discrete thing, quantum jump like discrete jump, one state to another. So discrete variable quantum key distribution is more intuitive to follow, easier to follow. That is why most of the time when I talk about this discrete variable quantum key distribution, unless until one is really like interested in continuous variable, some specialized terms.
Linear soluble are physically easy to realize.
Easy to realize, okay, but like how it is quantum, that understanding to appreciate that becomes difficult when it comes to continuous variable. Okay. So, this is a QKD tool. I already told no cloning theorem. Suppose this is the diagonally polarized state of a photon, it cannot be copied. Okay. So, you can't make copy. Okay. And like you do not know whether it is diagonally polarized. If you know that, then you can copy, you can make, but it should be then you can make copy, but it should be like arbitrary state. It's coming as diagonal sometimes coming anti-diagonal, sometimes coming linear. So, if without knowing about this state you can't make copy, arbitrary state, should be arbitrary state, unknown state, you can't make copy. Then mutually unbiased basis, that is what you use. Okay. What are the mutually unbiased is written, outcome of measurement on a state is random for the basis which is unbiased to prepared state. What is the meaning? Suppose I talk of this polarization of photon. Okay. So, polarization is having two state, when it comes to polarization is two state basis. Okay. Means if you know the two states of polarization, you can describe polarization property of that state at that light, okay, that photon. So, what are these two states? It may be horizontal and vertical, this is rectilinear basis. Okay. It may be diagonal and anti-diagonal polarization. When I say polarization means field vibration in the direction, polarization I think all of you know, like field is vibrating in a particular direction, okay, electric field. So, and photon is also associated with field, okay, it's you can quantify. So, photon is like some field is associated. So, then you have like polarization state. So, two state basis. So, I say horizontal and vertical rectilinear basis, diagonal and anti-diagonal is called diagonal basis, or you can have circular basis right and left. Okay. So, most of the time we use this rectilinear basis and diagonal basis. Okay. So, if you know these two states, you can describe the polarization property of light. So, suppose I take I prepare my state in diagonal basis, means D and A. So, I prepare D, it is in diagonal basis, and I use this rectilinear basis I want to measure. Okay. I prepared in basis diagonal basis, which is D diagonal, and I am going to I am measuring in rectilinear basis. Okay. So, what it will happen, I will get random results. So, when it is random, you can't extract any information. Okay. That is the meaning, random, you can't extract any information. So, that is the thing. Same way, if I prepare rectilinear basis, okay, it may be H or V, and I choose to measure this basis, I am measuring in this basis. What do you mean by measuring in this basis? You may ask here, nobody is asking. I choose this basis, I will get random results, sometimes D, half randomly D and A, diagonal and anti-diagonal. So, this is called mutually unbiased basis. Okay. If you select another basis, you will get random results, you can't extract any information out of it. Okay. You can say, what do you mean by measure this, how you are measuring? So, basically polarization, that is why you are using this polarization thing. Most of the time you will see this discrete variable thing, people are using polarization. So, polarizer, linear polarizers are there, if you know. Okay. So, you can easily select like your polarization axis is there in this, they are the basically some material, okay, which do not let pass this, suppose I say horizontally polarized, light is. So, you have a polarizer or this is the element which will not allow to pass any vibration of this kind, only it will allow this if it is linear polarizer for horizontal. So, it will allow only this vibration of electric field to pass through, it will not allow other vibration. So, it you get or then when you say horizontal, it like it will pass this, vertical this. So, it is a linear polarizer, okay. You can keep on changing the direction, accordingly you can select this, okay. So, that you can do easily. So, if a photon is coming,
How to decide which basis function to be used?
random, it has to be random, it has to be random. So, I say suppose this is diagonal polarized light, okay.
Sir, but will that affect the outcome, final outcome? If you are selecting the basis function randomly, will that affect the outcome?
You have to generate random key, so that everything has to be random selection.
Fine, but when we are starting with a random, is it going to hamper in any way the efficiency of the output?
No, that is what you are interested, depends on what you want to do, depends on what you want to do. Suppose you want to generate random key, it has to be random. Suppose you want to do something different, okay. Suppose you want to have just horizontally polarized photons, you can't do that, then you have different process, okay. So, suppose I am getting lot of like something this direction or some this direction, but if I put here some polarizer, okay, which will allow only this direction to pass through. So, all will be cut or some component in this direction will be selected, some component in this direction. Suppose like this, so it will have very small component in this direction, larger component in this direction. So, that is what, so that is how you select and that is what you measure. You keep on changing the direction of linear polarizer, that will select. And then any measurement perturbs the system, okay. System is perturbed, like you know Heisenberg, if you measure one variable, conjugate variable, you can't measure it. So, it basically it changes the system measurement, that is how you can't measure. So, here it is written also. Oh, what happened again, connection gone or oh, sometimes it happens, I do not know why. Oh. Coming. I should not touch much, yeah. So, here is an Alice and Bob choose random basis, okay, it is written.
So where this LCP is working?
Pardon?
You are Alice and Bob are choosing basis randomly.
So, how they are selecting randomly, you are saying?
That you said that.
Hmm.
you
Hmm.
select. But you said this is the application of no cloning theorem that this will be secure because of no cloning theorem. So where this no cloning theorem is interplaying with this
Because so Eve comes into play, always there will be eavesdropper, okay. You want to have secure communication, somebody wants to see what you are communicating, that is why eavesdropper or hacker, they come into picture. So, if eavesdropper wants to have information what you are sending, try to measure, if you are sending through quantum state, they will get wrong result or they will introduce error, and that error you have put a threshold, you will come to know somebody is trying to have some mischief, listen, somebody is dropping, so you will stop.
no cloning theorem says eavesdropper can never copy.
They will try to make copy, no, they will try to measure, first they will try to measure, suppose they measure, and then I will see how eavesdropper can create problem, okay. So, they are not making copy, they are making measurements, okay. Whatever measurement they get, they will send that only, okay, without knowing its arbitrary state, they will make some measurement, quantum state is there. Suppose I know I am eavesdropper, I know this communication is through polarization state of photon, I will try to measure the photon polarization, if I am eavesdropper, I will try to measure, I may get wrong result, and that I think this is the state, and then I will send, because I have measured it is gone now. So, I will prepare the same state and send, but because when I am measuring I have got wrong result. So, I will be sending some wrong state. There are techniques, okay, but that is what eavesdropper is supposed to be having enormous amount of technology, okay, supposed to be, which even does not exist today. So, that's taken care of when you do the privacy simplification error correction.
Sir, so in our traditional decryption based method, on decryptor end we have either symmetrical or unsymmetrical key. So we know which key needs to be used for decryption. Here,
Here it is symmetric, quantum means symmetric key only, symmetric. Till date quantum key distribution is symmetric key distribution, both the parties are having the same.
It is completely random, right?
It is random.
So how can a decryptor know whether he has used a proper key or not?
That is what I was telling, one question came again. So, you do the error correction, you compare the bits both sides, these random bits, then you do the error correction whether there is some mistake or not, okay, whether they are same or not. And then for error correction you have used certain bits, okay, that you have communicated ki I am checking, okay, for checking you have communicated to each other, no? You will have to communicate, how you will check, both the parties are separate parties at distance. So, they communicate. So, those bits which have been used for checking, you discard those bits. So, that is called privacy simplification. Whatever information you have communicated over public channel, you discard that, that is called privacy simplification. So, after that you get the same key, and that you can verify. Suppose you encrypt your message and then decrypt if you are getting correct message. So,
We need to keep trying.
Sir, here you have written any measurement and then you have written generally. So,
so non-demolition measurement are there, okay, although not very popular now because we have to develop technology. So, using non-demolition measurements you can have like without demolishing the state, yeah, you can do that technique. So, whether we should take a break here and then
Yes, cup.
Just check if tea is outside.
no, otherwise we can have थोड़ा पानी है क्या कहीं रखा है, थोड़ा पानी पीने की ज़रूरत है. Thank you, thank you, thank you. नहीं, ठीक. So, how do you do this quantum key distribution which is like most visible application of quantum communication? How do you do that? So, basically we do experiments. I am not a theory guy, not very good in theory, that is why I finish very fast this Shannon entropy and all those things. Otherwise we would have talked channel capacity and all those things, okay. I did not talk about those things. So, we do experiments in the lab and that is what Quinstenden, like Dr. Quinstenden told that we are making kits also. So, we are basically experimental guys. So, how do you do that? I told you, you have prepare and measure based protocols and entangled photon based protocols, okay. So, here most of the time you use weak coherent pulses or weak coherent states, okay, prepare and measure. So, what you do, you take a pulse laser, okay, laser can be CW continuous wave and pulse, okay, like your pointers most of the time they are CW, but you can have pulse laser. When you do the surgery and all, you use pulse laser because pulse laser will have more power, okay, it is concentrated there. So, you can have a pulse laser and then you reduce the intensity of the laser using attenuator, that is called attenuator, which reduces the intensity. You attenuate in such a way that on average there is no more than one photon in a pulse, okay. So, it is called weak coherent pulse. So, it is approximation to a single photon source. in prepare and measure protocols, you are supposed to use a single photon source. Okay. In prepare and measure protocols, if you want to have secure communication or to ensure security, you have to use single photon source. Okay. But instead of using single photons, most of the implementations, commercial or otherwise, lab implementation also, they are based on weak coherent pulses, which are approximation to the single photon source. Okay. They are not single photon source. Okay. This weak coherent pulse is not a single photon source. Okay. This is weak coherent pulse, laser whose intensity has been reduced by attenuator, and it will follow different photon statistics. Okay. If you want to measure photons, number of photons coming at different time intervals, you plot a distribution, it will follow different photon statistics compared to single photon source.
Each pulse will have energy h nu almost approximately.
Each photon will have energy h2, not
And
pulse. Yeah.
As you said, it is approximately.
Approximately. So it will have that. And then you can have single photon source that you can use here for prepare and measure, or entangled photon source. Okay. So these are the sources. So how do you develop entangled photon source? You use laser, you use nonlinear crystals, nonlinear optical crystal and nonlinear optical crystals, and then you suppose you have laser at 405 nanometer. Okay. So when it passes through the nonlinear crystal, nonlinear optical crystal, this one photon of the laser breaks into 2 photons of lower energy. Okay. And this lower energy photons, they are produced at the same time. Okay. In presence of crystal, non-linear optical crystal, N for non-linear optical crystal. Okay. So non-linear optical properties. There are linear optical properties, means response is linear, which light is coming, output light linear, but non-linear response means light is coming, output is non-linear, behavior it will show output non-linear. Some light is coming, how it is changing, okay, after the crystal. So that is why non-linear optical crystal, response of the incoming light is non-linear after that. So you have 2 photons coming together, because they are coming together and they are being generated at the same time in a pair. So if you detect one, okay, so presence of this one photon heralds the presence of another. Okay. It guarantees that another photon is there, the pair, because they always come in pairs. Okay. So that is called heralded single photon source. So you can use heralded single photon source here instead of this weak coherent pulse. Okay. Or you can have these 2 photons which are coming. If you measure their properties, if you measure some property of these photons, suppose polarization, okay, or some other property you can measure. Suppose you are measuring polarization and they show correlation, they are correlated in their polarization properties. Okay. If this is horizontal and this is again horizontal, or this is vertical, this is vertical, this is horizontal, this is vertical, so they are correlated. Okay. If they are correlated in polarization, we say they are polarization entangled photons. Okay. We can't say, suppose we are measuring polarization, we can't say that they are time being entangled, we can't say they are energy and time entangled, we can't say they are orbital angular momentum entangled. Whatever property we are measuring and looking at the correlation, they are entangled in that only. So measurement is very important in quantum mechanics. Without measuring you can't say, I can't say I am measuring polarization correlation, I can't say they are entangled in it. So measurement becomes very important. So that is how you create entangled photons. We will get into more detail later.
Sir,
Yeah.
when the light passes to the another crystal,
Mm-hmm.
you mean that it is generating the second Hawking generation?
No, so both the process can take place, this is not, this is reverse of second harmonic. Okay. This is a quantum mechanical process, spontaneous parametric down conversion, spontaneous, it is spontaneous parametric down conversion. So, here a down conversion is happening. Okay. Second harmonic, it is up conversion, like second harmonic means omega, 2 omega. So, energy is increasing. Okay. So, 2 photons of laser, they combine to make 1 photon after the output. This is again nonlinear crystal, nonlinear process, 1 photon of the output. So, that is 2 omega. So, up conversion. Yeah, that is second harmonic, but here it is down conversion. Okay. So, it is now omega by 2 omega by 2. Okay. That is reverse and is spontaneous. So, its spontaneous emission is quantum mechanical process. Vacuum, presence of vacuum is very important. Vacuum does not play any role in second harmonic generation. Okay. But without presence of vacuum, without vacuum fluctuation, you can't explain the spontaneous emission, spontaneous parametric down conversion. So, it becomes a quantum mechanical process. Okay. Second harmonic, if you see second harmonic light and study the photon statistics, okay, it will show classical source property. Okay. But if you study the Herald single photon source which we have make using SPDC, it will show, it will act as a quantum source, photon statistics will be completely different. So, using photon statistics you can find out whether your source is classical or quantum, or you can like coherent, it is coherent, what kind of photon statistic will be there. If it is thermal source, what kind of a classical source, what will be the photon statistic. If it is quantum source, what will be the photon statistic. So, when you say all those things you can verify. Okay. So, for that you have to measure intensity correlation. Okay. That is called G2 tau. You guys can see there this thing. So, G2 tau, okay, that is called intensity correlation. Okay. So, that is what you measure, and how do you measure that? You measure using Hanbury Brown twist, or suppose you have so you have photon coming here, okay, it will pass through or reflect. Okay. If photon is coming here, it will pass, okay, or this is beam splitter. Okay. Either it will pass or reflect, and you have detector here, single photon detectors. If it is single photon, what will happen? It will either reflect or pass. Okay. It cannot do both, it is single photon. So, if you measure this coincidence detection, so at a time there will be only one click, there will not be coincidence detection, coincidence detection will be 0. Okay. So, G2 tau will be 0 for a single photon source. So, that is called, and it will follow. Suppose you are here measuring, so in time you can record photon, how at what time photon is coming. Suppose I record for 20 nanosecond, okay, this number, and then another 20 nanosecond, again number, again 20 nanosecond, another number, and I plot this distribution arrival of photons. So, that will follow sub-Poissonian statistics. Okay. That will follow sub-Poissonian statistics. Sub-Poissonian, and if it is laser, suppose instead of single photon I put laser here, again I have detector, okay, and when it is laser it will go both way, okay, it is not single photon, and then again I follow this photon statistics, okay, and then distribution will be Poissonian. Okay. And if it is thermal light like this light and it pass through beam splitter or without beam, I measure the again 20 nanosecond 20 and then plot the photon statistics, I will get super Poissonian. Okay. So, Poissonian is certain width, sub Poissonian smaller width, super Poissonian larger width than the Poissonian. So, that is what you, that is how you verify whether your source is classical source, thermal source or quantum source or coherent.
We measure both and we plot how many we have received.
For photon statistics you can measure just one or both also, not a problem, and at time certain time in bin you measure and then plot the distribution number how they are distributed in different time intervals. So, sometime it will be like same time it will be 10, sometimes 15, sometimes. So, if you plot the distribution over time it will have certain distribution and that distribution will be Poissonian, sub Poissonian or super Poissonian depending on which source you are using. So, that is how you distinguish between different sources of light by photon statistics, measuring photon statistics. And if it is laser, that is what I was going to, that is why I went there. If it is laser, you are reducing the intensity, you can't change the photon statistics. Okay. It will remain Poissonian. It is because it is laser, a source characteristics you can't change by reducing the intensity. So, it will remain Poissonian distribution still, if you plot that photon statistics for weak coherent pulse it will remain Poissonian, while for single photon source it will be sub Poissonian and coincidence count is 0 G2 tau. Okay. Like anti bunching, for single photon source it will show anti bunching. You can there are two ways to verify. You can do intensity correlation or statistical distribution of photons. Okay. So, in different one time interval you chase and then do the distribution. So, that is how you get sub Poissonian, Poissonian all. Or you can measure this intensity correlation. Intensity means photon count, in terms of photon counts you do intensity correlation. If G2 tau is 0 means
Only
one photon at a time. So, it is single photon source, quantum source. If G2 tau is equal to 1, okay, it is laser coherent source. Okay. If G2 tau is more than 1, okay, it is thermal. Okay. So, again using intensity correlation you can verify or using statistical distribution of photons. Both way you can verify whether it is which kind of source you are using. So, and so what I was saying, so it is laser when you do the weak coherent pulse it will remain Poissonian, it is not a single photon source. Okay. While single photon source will have sub Poissonian or intensity correlation will be G2 tau will be 0. For laser it is G2 tau is equal to 1. If you measure intensity correlation of weak coherent pulse you will get 1 only. Okay. It is very different source, it is just approximation to a single photon source. Okay. That is why there are certain security issues when you are using weak coherent. Pardon?
Which kind of statistical distribution you are talking here? You are talking about this in time, I mean arrival?
In time of arrival. Yeah. I select a certain time bin, okay, and I
So, it is a Poisson process.
yeah, Poisson. But this distribution if you plot time it may become sub Poissonian or super Poissonian. So, this is very important. Most of the engineers because you guys from engineering background, most of the engineers they take it as single photon source. Okay. They say we are using single photon source, but when physicists are there they say what you are talking, it is not a single photon source. So, it can never be single photon source, but engineers even like you British Telecom head was talking, okay, they are doing quantum key distribution in UK and all. It is a single photon source we are using. You can't say it single photon source, you call it weak coherent pulse, that is all. Okay. Single photon source is completely different entity. Okay. So, that one should understand, difference one should know.
And the company in Bangalore, QNU Labs, what are they using?
Most of the, not only a QNU lab, either Toshiba, ID Quantic, all these global giants which are involved into this quantum key distribution, they are using weak coherent pulses only. Okay. All the commercial implementations, they use weak coherent pulses only, and they, if you talk to engineers, their marketing or technical aspect, they say you are using single photons. These are not single photons. Work is going on for single photon source, but
Reason for that?
huh?
Why they are not using single?
Very right question. Why? So, here you see that we are using non-linear crystal to generate Harald single photon source. Okay? And efficiency of this generation is not very high. Out of 10 power 8 photons or 10 power 6 photons, only 1 photon will get converted. So, this pair generation rate after this, it is not very high. We are limited in number. It will be million or 10 million, something like that, 10 power 6, 10 power 7 per second. Okay? Even if you are very highly efficient nonlinear crystal. So, per second we can't have more than that if you are using this nonlinear crystal. Okay. And other, they are making other methods they are using to generate this single photon source, like quantum dot and all. Again, that not very efficient process. Again, they are getting very small number, 10 power 3, 10 power 4, something like 10 power 6.
What practically we want?
Practically, and then why weak coherent pulse, first let me tell you. So, weak coherent pulse, you can have modulation at the gigahertz rate, 1 gigahertz, 10 gigahertz and all. So, 10 gigahertz 10 power 9, here is still at, and 10 gigahertz 10 power 10, here you are still at megahertz level. So, you get much higher key rate compared to that, okay, if you are using that. Pardon?
You are mentioning coherent states.
Weak coherent states, yeah, weak coherent state. Yeah. Coherent state you are saying, na? Coherent state. So, laser is basically coherent state. Laser is basically coherent. That's how this coherent state came, because of laser, to explain the property of laser.
Are you using any property of a coherent state in this communication business?
Certainly. The moment you use the lasers, it's coherent state. So, you are using property of laser.
Using a laser.
Hmm?
If I'm not using a laser,
Yeah.
how, in which way all this will be affected?
If process will be less efficient. Okay, process will be less efficient. If you are using laser, it will be more efficient. And all these generated photons, suppose nonlinear crystal and all those things, their property is governed by the source. Okay, their coherence between these two photons will be different. Okay, if you are using some other source, you are not using coherent source. Because now you can have this using LED also, you can have. Okay, and recent papers came, they have used sunlight to do this down conversion. Okay, so you can use, but process will be very inefficient. I am saying when you are using laser and highly efficient crystal, you are getting 10 power 6 or 10 power 7 photons. There you will get hardly 2 photons, 10 photons, 100 photons maximum per second. Okay, very less. So that's the problem. Otherwise, you can use it.
Sir, if you are
Yeah.
using the envelope crystals,
Hmm.
vacuum crystals, I think 2 photons of same frequency are colliding, and you are getting the single photon of twice the energy.
No, that is second harmonic. That's what I told you.
But sir, I think in that case there is a specific requirement of the power level only. Then only it can generate a then only it can
Second harmonic.
second harmonic.
Second harmonic.
2 photons of same wavelength or frequency.
Combined to make higher energy photon.
Output is a single photon of
Higher energy, higher energy.
I think as per sir asking, there is a requirement of laser only in that case. In the case of NL only.
But in the down conversion,
Down conversion, it's not compulsory to have laser. It's down conversion, okay, and it's spontaneous emission. Okay, spontaneous emission. It's coming out of spontaneous emission.
possibly the cross section of the probability of down conversion, I mean generation of 2 photons might depend in some way on whether the input state is coherent or not.
Yeah,
Might.
efficiency, like, yeah, it will depend on input state is coherent or no.
And the envelope crystals, sir, I think they are non
depending on you want to have chi3 or chi2, okay, centrosymmetric and non-centrosymmetric, which process you want to use. Okay. You can have centrosymmetric or chi3 is less efficient compared to chi2.
Doctor saying that T is served, so at a logical point we take a break.
So, I will talk about this thing, then this slide, then we can take a break. Okay. So, this is source, then you have, because we are using light photons for communication. So, you can have optical fiber or free space, that we have already talked about. Then you have, if we are using this photons, okay, you have to have detect the photons. So, single photon detectors you need, and single photon detectors, they can be avalanche photodiode based, okay, APD based, and they can be superconducting nanowire. So, they are utilizing property of superconductivity, superconducting nanowire single photon detectors. So, you can use this too, and this is for when you are using photons. For field quadrature, if you are measuring continuous variable, you have to have homodyne detectors, okay, and again there weak coherent states you are generating, and or squeeze light you are generating, and this also can generate, this process can generate squeeze light, then you use homodyne detectors. Okay. So, this is the basically this kind of detections, and light there also is continuous variable electronic field, you can take through fiber or free space, either photon or continuous, you can channel through free space or fiber. Then if it is continuous variable, you use homodyne detectors, and if it is single photons, you use single photon detectors based on avalanche photodiode or superconducting nanowire single photon detectors. No, this is superconducting nanowire single photon detector, it is not homodyne detector. It is utilizing the property of superconductivity. Okay. Discrete only, for discrete. This is compact and cheaper, okay, not so cheap, but cheaper compared to that, and this is like 1.5 to 2 crore. This will be around depending on which wavelength you are selecting, it will be 6 lakh to 25 lakh, okay, this, and that will be, and this is compact, this is bulky, because you require cryostat, you are using superconducting. So, superconducting still you require helium, okay, cooling. So, you require cryostat and all those things, pump, cryostat and all. So, it becomes bulky and costlier also.
Are they actually speed in single photon?
Pardon?
This is single photon detector, right?
Yes, single photon detectors.
It is actually just now you mentioned that.
Okay, single photon detectors, these are the click detectors. Okay. Suppose this APD based single photon detector we are talking, suppose at the same time 2 photons are coming. So, APD detector, this single photon detector cannot distinguish whether it is single photon or 2 photons. It will generate a pulse, okay, in response to that. But there are photon number discriminating detectors, okay, but still these photon number discriminating detectors, they can't discriminate between 1 to 5 maybe at the maximum. Whether we have got 1 photon, 2 photon, 3 photons, 4 photons, 5, we can't distinguish much larger numbers. So, you can have photon number discriminating detectors, you can discriminate how many photons have arrived, but that is the catch, even 2 photons are coming at the same time, this single photon detector cannot say whether it is single photon or 2 photon.
And between the two, you talked about disadvantages of the single photon superconducting nanowire, but you have not talked about advantages.
Advantage also I will talk. Okay, very good you have asked. The advantage here, this date time, okay, date time is higher, here date time is much lower. Suppose 1 photon comes, it generates a pulse, okay, electrical pulse, and then it will not respond to the incoming photon immediately, okay, only after certain time it will respond, okay, this single photon detector based on avalanche photodiode. So, most of the time it will be 20 to 30 nanosecond of the order, okay, but here date time is very small, 1 photon comes, it generates some current, again very fast it will go to the normal state, again second photon. So, date time is hardly 1 to 2 nanosecond, 1 to 2 nanosecond, and then here this jitter also larger, like uncertainty in the time, So, here jitter is smaller. So, here it is like superconducting, superconductivity. So, it will change the resistance when photons come, its resistance, it generates the electron, it will change the resistance, okay, this, and it is based on the superconductivity, changing the resistance, and then that resistance will change the current pulse that we measure. Here it is avalanche photodiode, if you know avalanche. Yeah.
This nanowire means indicates the size of wire.
Size of the yeah, wires, yeah, it is a nanowire. You draw nanowires and hits the nanowire, because if it is not nanowire, suppose it's larger strip, so from different which are uninterrupted photons will be also detected. So, reduce the background or unwanted detection, you take it very small. Even in this kind of detectors, aperture, active aperture is very small, some microns only. Okay. Here it is nano, yeah, you can control, and here it is active aperture is around 125 micron, 100 micron, something like that. If you have very high aperture, suppose this detector aperture is high, you will have lot of background and all those things coming.
Can you repeat what you said about jitter? I didn't understand what is jitter.
Jitter means you are measuring the, suppose for this quantum key distribution in many process, you want to have arrival time, you want to record. Okay. So, here arrival time recording will be that jitter will be there, okay, some with how much certainty you can record the time. Here it will have less uncertainty about the time when you record, that will depend on the timing electronics also, both combined, both will play a role, timing electronics, okay, which is recording the time, as well as this process which is generating the electrical signal, okay, electrical signal is being generated, that is what you detect basically. So, here electrical signal, so that process itself will have certain timing accuracy. So, that is the problem. So, recording of time, how accurately you record the time of the incoming photon.
And what are CUNY labs using among the two?
CUNY labs, all the commercial implementations still they use APD based, because this is slightly cheaper, compact and all, that becomes important.
So who will use these, or when will this become commercial?
This will become commercially, like where you have very photon hungry, like suppose satellite based quantum communication, you have to have optical ground station, and there you have already some attenuation is happening, okay, over the atmosphere. So, you can get, or you want to increase the rate of this key, then you can have superconducting. Okay. Suppose you have to have higher key rate, okay, then you have to go for that. Suppose with this key rate is good enough, whatever you are measuring, you can go, but if you want to increase, you have to have, because dead time is smaller. So, you can have larger number of photons detected. Here dead time is larger, so you have this number.
This free space communication involves entanglement?
Anything, entanglement, weak coherent, anything you can do. Whatever you can do with fiber, you can do with free space. Whatever you can do with free, you can do with fiber, because both can take the light. Okay, doesn't matter.
In free space, when we transmit, so will it not lose its properties in the channel?
We will discuss that. Let us have tea break now. I have finished this slide. We can discuss that. Yeah.
You can take after a break
Hmm.
also. Since on one side you are talking about no cloning theorem,
Mm-hmm.
but at the same time for implementation of communication we will need repeaters.
Repeaters we talk. Repeaters, what it does, it doesn't clone the state. Doesn't clone the state. Repeaters. Repeater will store the state. Okay. Repeater will store the state and then transmit it again. It doesn't clone. Without cloning, it is storing, okay, and then transmitting to further.
Storing then transmitting.
Hmm.
While storing, if you do entanglement,
you use entanglement, basically this storing and all those things repeaters, that is what I am saying. Till date you are using weak coherent pulse for all the implementation. If you want to have this storing, retrieving, repeater thing, you have to use entangled photons, that is a problem. Till now nobody is using entangled photons for commercial implementation of secure communication. If you want to have network where fiber network, global network, you have to use repeaters, and if you want to use repeaters memory, you have to have entangled photons. With weak coherent pulse you can't do that, or single photons. Why entangled photon, single photon source you require when you are using quantum repeaters? Because if you are using weak coherent pulses, this is a mixed state, mixed quantum, it is not well defined state. Suppose you store and then retrieve, so you can't define whatever you stored here because it is not well defined. So what you are storing, what you are retrieving, you do not know exactly, unless until it is very well defined state. Entangled state you know, single photon state you know. So whatever is storing you are retrieving, or you can have some error correction thing, suppose some but you have to know the state. So all those things, if you want to have global network using quantum memory, quantum repeaters, it is going to be based on entangled photons and single photons. You can't use weak coherent pulse. Till now we are very behind still. So technology, lot of things have to be done in quantum communication also. Okay, it is not like we are very primitive stage still, like quantum computing. So quantum technology is still in very primitive stage. It is not like हम बहुत पीछे हैं, everybody is पीछे. Okay, there are so many things need to be done, and if you start working you can catch up very fast. Okay, it is very primitive stage still, either quantum sensing, quantum computing, or quantum communication. We are very lot of things need to be done. Okay, and which can be done, it is not with proper support. So field is open, it is not like that कि आप तो बहुत पीछे हो गए अब तो हम कर नहीं पाएंगे. It's not like that. So many things have to be done.
On that optimistic note, let's take a tea break. It's 11:40 right now. Let's take a 20-minute tea break
Yeah.
and we come back at 12. Then we will have about 1 hour
photon, it's still detectors are not easily available at research stage only. So, that is a problem.
Why is it more difficult to work with longer wavelength?
Longer wavelength, how you conceive like something which is like macroscopic thing, size, how you conceive it as particle thing, and there it becomes problem. When you say single, so it has to be behave single. When you are such a big thing, meter suppose radio wave, microwave, again you go to radio wave. So, how you are going to have measure it as a photon, which kind of detector you will have. So, that measure single photon. So, those things become difficult, how to develop detectors, how to quantify them as a photon. So, that is why things are not available, but I have been thinking, I have been discussing till now all this modern quantum optics. Okay. It all started with Hanbury-Brown twist experiment. Okay. And Hanbury-Brown twist, they were astronomers, basically radio physicists. They were working on radars in war, okay, Second World War, and then World War got over, they started working on astronomy, astrophysics. Okay. And they developed this intensity correlation thing, okay, for radio waves. Intensity correlation they developed for radio waves. Radio antenna, they were yeah, intensity correlation, Hanbury-Brown twist, they developed for radio waves to find out the size of stars, okay, and they were able to measure, okay, radio waves. Radio antenna they were using, and they could correlate the intensity of radio waves coming from star, and from that this coherence thing, coherence length they could measure with intensity correlation, and with that coherence length they could measure the size of stars. They thought that if radio waves, they are electronic waves, okay, why not this optical thing, there should also be correlation, and then they measured, did the lab experiment with a sodium source, sodium lamp using filters and all. They observed that they are correlated, even this sodium lamp, and they observed intensity correlation in that lab experiment. Then they thought, now we have done this lab intensity correlation for sodium, let us use optical wavelength for intensity correlation, find out the size of stars. Then they use optical domain, and they could find out the size of stars. So, size reduce everything. Okay. Now, and that was the basis, like intensity correlation thing. Okay. Yeah, basically Hanbury-Brown twist, they were astronomers. Okay. Intensity, you are measuring a signal, you measure intensity basically, that is what. So, intensity correlation IT plus tau, intensity measured at time t and intensity measured at time t plus tau. Yeah, intensity measured at point I r1, intensity measured at I r1 plus r. So, that, so you can have basic intensity correlation, okay, in time r position. So, that is what. So, using that intensity correlation they could find out size of stars, and they could see optical domain also. Okay. So, they could see the correlation. So, now I say many discussions, if Hanbury-Brown twist from radio wave they could see in optical domain, okay, some correlation, why not this optical domain correlation which entanglement we see, why can't we have entanglement all those things in radio and macro, okay. It should be there in principle, but how to measure, how to create and how to measure, that is the problem. Till now it is not there. People are trying to observe in microwave entanglement, but in continuous variable domain, okay. Field quadratures, they are field, because field I told you can measure field quadratures, homodyne and all. Using field quadrature measurements, they are trying to measure entanglement in microwave, but radio is still very far. So, but discrete variable when it comes to photon, still it is not there in microwave. Okay. So, these things are there. In microwave they are trying to observe, but measuring continuous variable field quadrature measurements using homodyne detectors. As a discrete variable photon, still it is not. Entanglement, you see, When you talk of entanglements, it's two parties involved, okay, two parties. But nowadays they say ki even if two variables are entangled in the same system, they call it entanglement, but it will not show the non-local. Yeah, that is the problem. So, where you want to use it, whether you require non-local correlations, then you have to have two parties, you can't do that. Okay. If you want to use some technology or something, some system you want to develop where non-local correlations are very important.
What you need is two degrees of freedom. So from one
Yeah.
particle you can
So, if it is not important for you, non-local correlation, space separated correlation is not important, then you can use two variable entanglement or two variable correlation in the same system, yeah, depending on what you want to do, and people are utilizing that property. Okay. But in true sense, non-locality is the basic property of entanglement to verify. So, that is not being used when you are talking of single system two variable.
2 degrees of freedom you want.
Yeah, 2 degrees of freedom, yeah. So, things will come as you asked, Kunj. So, but still far, yeah, it is possible. I go and ask people, can you generate this nonlinear, you can generate radio thing, how you measure, but still they are, because radio, there are so many experiments going on. You see radio, this very important for defense, so many big projects. Anywhere you go, IIT Roorkee, there are so many, triple IIT and even SRM, there are so many guys having big labs in radio they are working. So, I asked them, can you generate this kind of thing, but still not much progress. So, as I showed you, you can have free space as a medium or optical fiber, both you can use. And why free space, our satellite is much more important. Without that you can't have like a global network, and without global network it has no practical value. When I go and talk, if you secure your communication between just 2 points or 3 points or 5 points, it does not make much sense in today's world, okay? Because everyone is so mobile. Today I am in Pune, tomorrow I will be in Ahmedabad, I will be going to Bombay, then I will be going to Calcutta, I may be going to Berlin, I may be going to London, anywhere, okay? So, everybody is so mobile. So, just securing 2 points communicate, it does not make sense, it has to be a global network. Okay. If it has to be global network, just using fibers it is not possible. Why it is not possible just using fibers, this quantum communication network or quantum key distribution network? Because fibers has certain losses, base of the fibers have loss, okay? And so, if you are sending your photons quantum state through fiber, they get lost, they get attenuated, they get lost, okay? Absorbed or whatever, because of loss they get lost in the fiber. So, you can't take them very far, okay? In classical, you say classical they use fiber and pura network hai fiber based.
Classically you have intense.
So, in classical you have boosters you use, not many photons, use boosters at 10 to 15 kilometer you use boosters. So, you amplify and you use regenerative repeaters, both you amplify then regenerative repeaters. So, it is kind of classical repeater, okay? You amplify and then do the error correction. This regenerative repeater that does the error correction, whatever errors come in digital thing, it corrects that, okay? So, and then amplifies, so it boosts the signal after correction. So, so you use that, but in quantum, when you are sending quantum state, you can't do this boosting. Why you can't do the boosting after 10-15 kilometers? You may ask, no cloning theorem, you can't make a copies of arbitrary quantum states. So, no cloning theorem prohibits you to do the boosting for quantum states. So, you can't use fibers for very long distance quantum key distribution.
So is the attenuation of a classical signal in fiber similar to the
Similar,
it that does
does not matter, but because you can always amplify. you can boost the signal, but in quantum you can't boost the signal. So, like classical repeaters,
And as a thumb rule, what is the typical
it is 0.2 dB, but now they are getting up to 0.18 dB to 0.16 dB. They are working for even lower losses, they are per kilometer. Yeah. So, that is the problem. So, you can't use a boosters amplifier for quantum states. So, you can't take them. No, still there are no quantum repeaters. Still,
Suppose I use entanglement, like entanglement swapping or teleportation or something like that. You can at the places
you have to have a long distance. So, you have to have quantum memory along with entanglement swapping and teleportation. So, this good quality quantum memory is still not there. Okay, they are in researches. They are working on. There are few companies along with NIST and other agencies. They are working research groups. So, they are working for this quantum repeater, but still it is not available. It is still research stage only. So, you can't use that fiber for long distance. Okay, that is why you have to use, when you want to have long distance quantum communication or quantum key distribution, you have to use satellite. Okay, you can see that for 500 kilometer, suppose you have distance telecom fiber. So, losses will be very high. Okay, and for free space losses will be very less. So, that you can do that, and you can see that through satellite you can have this kind of key distribution. Okay. You can say ki somebody was asking atmospheric problem will be there, some attenuation will be there through atmosphere. Somebody asked this question. Okay. So what happens? Fiber, when you use atmosphere, okay, for satellite long distance, for long distance communication, our average atmospheric height is 12 to 15 kilometer only. Beyond that it is all free, nothing is there. So, all the attenuation disturbance happens only in 12 to 15 kilometers, okay, and but fiber it is all along, okay, if you are taking. So, that is why even this atmosphere is there, still you get good signal, and you get this, you can do the quantum key distribution, quantum communication using satellite. Okay. But depending on atmospheric conditions, key rate will be different. Okay. Suppose its pollution is high, that also we have studied, pollution is high, aerosol load is high, there is more turbulence atmosphere. So, because of turbulence, refractive index variation will be there, dithering will be more, signal will be less, which you receive at the ground. So, you will have key rate or link efficiency will become poorer depending on atmospheric conditions. So, we will have less key rate, but it can be done. They have done, and you can have network of satellite, just not one satellite, and you can have using network of satellite you can have like global quantum communication network, and in between you can have fibers. Okay, you can have fibers, you can have satellite, you can have LEO, you can have MEO, GEO, all those things. Okay. Why directly you can't use GEO all the way? Why you used to have GEO then LEO and all? What is the problem? Distance. Distance is fine, but what is like, what will prohibit?
Stationary.
There is one more subtle point here, why you can't directly GEO or MEO, why you are not using, because photon, okay, which is coming, that will have same divergence which is the divergence of laser from where it is being produced, same mode, okay, will have same mode, spatial mode, which is being used to generate that photon, it will have same spatial mode. So, it will have same divergence. So, and divergence is like basic property of the light beam, okay, light beam laser. So, it will have same divergence. So, by the time if you are sending from GEO, by the time it will come to ground, it will have so huge divergence because this catchment. So, you use very large telescope, okay, which is not feasible. Even for LEO, it is footprint of the divergence, the probability of catching a photon, that becomes more than few meters, okay, even for LEO, where we are talking of 500 to 800 kilometers. So, that is the problem. So, directly you can't geo. So, you first take here geo, do the divergence check again, then you send ground. Okay. So, that is why you need geo, MEO, LEO. If you want to have, like, MEO means medium Earth orbit, geo means geostationary.
So at LEO you will still need that few meters diameter.
Yeah, not few meters, but you can arrange with 1 meter 80 centimeter with LEO. Okay. You can have sufficient signal. LEO to ground, that is what I am saying. LEO to ground, you can have few, like 80 to 70 centimeter or 1 meter telescope, you can have sufficient signal. So, you can have this network, that is the beauty of free space, okay, and you can have like combination of fiber and free space. So, how do you do this with satellite? You can have two ways, okay. You can use prepare and measure, okay, and protocol. Here satellite, there is device which is preparing the quantum state, you put that is payload device which is generating the quantum state, okay, preparing the quantum state, and it is being sent to the optical ground station. Optical ground station is what it is? It is a telescope, okay, large aperture telescope, along with pointing, acquisition and tracking, okay, facility. Pointing, acquisition and tracking facility means you can catch most of the signal which is coming to the ground, okay. That is what it does, pointing, tracking the position of telescope, using this pointing thing, and acquisition, you do proper acquisition, so that you have sufficient signal to noise ratio, you get most of the signal here. So, that is done, you prepare and you send, and then it is measured at the ground station. So, that is how you have key Ka, Ka, and then it goes to another ground station, satellite is moving. So, it connects with another ground station, this again telescope and PAT system, pointing, acquisition, tracking, and then it develops Kb. Once it has these two sets of key, satellite is having key information, but you notice that, and then satellite can send this and another jar operation. We have seen this x y in beginning when we are talking of, then another jar operation we will have, like here this is Kb is there, you send that, so it will do the jar operation and you will get Ka. So, now both the places, this is already having, this will also have Ka, okay, and now one can have this symmetric key is there, one can have secure quantum communication. So, this is prepare and measure, but satellite is having key information. So, you have to trust, okay, satellite is acting as a trusted node, you have to trust that nobody is having key information from the satellite, okay. And here this classical channel is one can use radio wave, okay, or optical, okay, laser comm, or this quantum is like quantum state. So, that is what. So, this arrangement works as a trusted node when you are using prepare and measure protocols, but you can have entanglement based protocol, okay. Here satellite is having source of entangled photons which are being sent, this pair which is being sent to two stations, and you make measurement on these two stations, on the photons on two stations, and this measurement on photons on these two stations, that develops the key. And here satellite is not having any key information. So, it is called untrusted node quantum key distribution. You do not have to trust satellite, okay. It is not leaking the information, this is better, much more secure, okay. Because nowadays we are having thousands of LEO satellites, you do not know how one can. Bangalore, Ahmedabad, you can have any station, just I have written Bangalore, that is all. So, you can have any station, you can have Leh Ladakh or something, yeah, Leh telescopes are there, then Ahmedabad
Is it
cycle.
country specific now?
It is country specific also, country specific in the sense China is having like now global thing, okay. They have connected through South Africa, China, okay, and they have connected to China again, Beijing, and then to Europe, Austria, Vienna. So, they have developed, now they are going to have Brazil also, Latin America. So, they are trying to have a global communication network.
Some geopolitics scenario,
Mm-hmm.
will we prefer country wise or we will rely on?
So, you have to have there is no point of having, that is what I am saying ki, tomorrow suppose our Abhi Prime Minister is going all along Australia, he is going to USA, he is going all the places, keeps on going around, and defense minister is going around. You want to have, how you are going to do? Suppose. So, just if your country you have to use some other you have to rely on somebody else network then.
Do these Chinese people use entanglement in this?
Till now these Chinese people are using weak coherent pulses only, okay. Entanglement they have used, they have demonstrated, but for communication network they are using prepare and measure. Through entanglement they are getting very small key rate, okay, very small key rate, okay. That is why they have not used entanglement based protocol for secure communication. They are using prepare and measure, because they were getting sizable key rate which can be used for. Satellite is, you need not to trust ki it is not leaking information, nobody is hacking, you do not have to, that is the meaning of, because it does not matter, it has no key information.
But they're sharing quantum photon 1, photon 2.
Mm-hmm. So, it has no, it's unless until measurement is done and keys are made, it does not matter. They are entangled pair, they are correlated pair. They are correlated pairs, yeah.
Weak coherent entanglement is not possible.
Pardon?
In weak coherent, you told entanglement is not possible.
Weak coherent is completely different source, entangled photon is completely different source. That is what I am trying to emphasize, like quantum source and classical sources. Weak coherent pulse is basically kind of classical source, okay. Basically classical source approximated is a quantum source, while single photon source and entangled photon they are quantum sources of light. You can't describe their properties using classical mechanics. Weak coherent pulse property you can describe using classical physics, okay. So, that is differentiate between quantum. Some sources property you can't describe using classical physics, that is quantum source. Sources property you can describe using classical physics, that is classical.
It is strong.
Hmm?
This one is which one?
This entangled photon source is a quantum source, okay. You can't describe using classical physics. So, again same recapitulation of quantum key distribution we have been talking about, okay. Information theoretic security to key is distributed, enables two parties, adversary can be detected by looking at the bound on the error, okay. That is why you have bound, you can calculate the bound. So, if error is more than that, you can like some eave is there, okay, eavesdropping is taking place, and you cannot copy, as we saw that no cloning, and there are mainly two categories of we have discussed already this anyway. So, what are the main pillars of security for QKD? They are entanglement monogamy, then mutually unbiased basis, we have talked no cloning theorem. What is entanglement monogamy, that I do not didn't tell, because that time I think we were not talking of entanglement based protocol, but if you are using entanglement based QKD quantum secure protocols, then entanglement monogamy is very important. Means, oh no, I should go to some seconds. Okay, this I have talked, this I have talked. I have come here, I think, yeah. So, this we have already discussed. Okay, I have to make it full screen. Oh, you must be wondering what is chapter 2 and all here. I will tell you what is chapter 2 and all here. So, this is basically I forgot to remove that. It's basically chapter 2 of one of the student thesis who has worked on this quantum key distribution. Okay, so chapter 2 there it's there. So, he prepared the slide for his PhD defense. So, I have just took it from there. So, this is these two things we have say, and this entanglement monogamy, if two parties share maximally entangled state, Alice and Bob, they are sharing. So, no third party can have can share this entanglement, this correlation. That is the monogamy. If couple is there, you can't have relation with some other person. So, that is the maximally entangled. That is why monogamy comes. So, that is how this you can use entanglement for secure communication, because third party cannot share the entanglement correlation. So, this we have discussed, this we have discussed. Okay. Now, we come to the BB84 protocol. Somebody is asking, will you explain BB84 protocol? So, this Bennett Prasad basically, and 84 is 1984, it was first presented in Bangalore. Okay. So, here this prepare and measure protocol, BB84 protocol is prepare and measure protocol. You can use weak coherent pulse or single photon source, okay, a single photons for this protocol. So, prepare, you are preparing random polarization states, random states of photon in polarization, okay, and then you assign bit to different polarization states of photon, and you this dice was random. So, randomly you are preparing, and for that you basically use random numbers, okay. We will see that how you generate random numbers and how you control. So, you assign these bits, then you communicate, then you send that polarization states of photons to the receiver, other party which want to have secure communication. So, this you have prepared randomly, and then this party selects random basis, these two random bases. This is called diagonal, this is called rectilinear basis, that is what they are selecting. Suppose this Alice has prepared state in diagonal polarized, and this Bob a receiver selected rectilinear basis HV. So, basis is not matching, so it will not, suppose some measurement will come. Once you measure, suppose you get horizontal, so you assign 0 bit, okay. Some result will come because he has sent D is like superposition of H and V. So, you will get some signal as when you are measuring HV basis, and then you assign this, suppose horizontal detector which is measuring horizontal polarization, that gives some detection. So, it will have 0. Then this is sending D again, suppose this L is, and Bob selects like DA basis, diagonal basis, and gets like D only in result, like clicks detector which is supposed to measure diagonal polarized photon, that only gets the click. So, then it will constitute a key. Same way like 1, okay, you have assigned to vertical, and then Bob is selecting rectilinear basis and measures vertical only, okay. Then you will get, suppose by chance sent V, and while going transmission it has flipped, it has come H instead of V, okay. So, it will have, then you will call, it will not be considered as, this will be called error, okay. You will have to do error correction, it will not constitute a key. So, if when you select the right basis, you get the key, and suppose strong state you get, then you you have to discard error correction.
How will we know that the bases are correct?
That you do like they communicate with each other using this classical phone line or internet or whatever. So, the classical communication, over classical communication they share the basis information, okay. It is all random. So, if basis and states are right, you get the key. So, how do you do that? Basically it is driving electronics which generates a random number, okay, and you have to have a timing information, okay, and then you, because BB84 this 4 polation state you use in BB84. So, you 4 polation state you generate and combine and then launch, okay. You can launch through fiber or you can send through free space, okay, it does not matter. So, here after this combining you can connect fiber line or you can launch through free space this quantum states, that is what channel, and then your basis information and all those things, timing information, this is communicated over classical channel, okay. And here after this comes to the another party, it has to be collected. So, you have collecting optics, there is launching optics, then you make measurements using polarizers because you are generating polarization states, and then single photon counting module or single photon detectors and timing information you record. So, these are the basic building blocks. Timing mismatch, then you will not have, like that will not constitute a key, means something else.
Here quantum channel, here classical channel, then their speed will be different. No?
Pardon?
One is the quantum channel, second is the classical channel. So the speed of
Speed is same, speed is same.
speed is same.
Fiber and electrical optical signal only, so speed is same.
Speed is same.
Processing may processing of classical information and quantum information may be processing time may be slightly different, but speed will be same over the channel because optical signal only, fiber and optical signal only. No? Quantum is basically photon and here you are using optical communication, normal classical.
But processing time will be different.
Processing depending on protocol and all those things may be slightly different, otherwise speed will be same.
Previous slide,
Yeah.
after classical communication we can know which bases are right.
Yeah, which will constitute the key. This is called shifted key. Up to here only, up to here I did not mention that, up to this place only when you are doing quantum key distribution, only up to this stage quantum mechanics is involved, okay. Beyond that it is all classical protocols, communication protocols. After that you do the error correction, that is low density parity check, most of the time you use LDPC protocol, okay, low density parity check, you include parity bits and then you check the error, okay, then you do the privacy amplification, okay. So, you do the error correction and privacy amplification, that gives you the secure key.
Bob knows the basis.
Bob has selected the basis, so yeah,
After
later after the classical communication.
Okay,
Once they know that they have taken the correct basis, okay, both have taken the same basis, then only they can extract the
so
key.
it's a time synchronized process.
Time synchronized, a time synchronized process,
And
yeah.
then we send the basis.
Yeah, time synchronization is very important, okay.
Then we ask, okay, select the ones.
Yeah. Time synchronization is very important, timing is very important here. So, that we discuss, okay, and so this what is the setup, okay, here you see here. So, this is FPGA board, okay. You can generate two random number generator using electronic process, or you can have pseudo number generator using that. There are LFSR and there are other techniques which can be used to generate this random number. And once you have generate random number, you can generate like accordingly this voltage pulses or electrical pulses, okay, whatever. And then these are the laser diodes, okay, diode lasers. We have to prepare 4 polation states, so we have selected 4 laser diodes, and you can do random switching of these lasers, and accordingly we have this polarization optics. Okay. So, accordingly we will have 4 polarization state random generation, because it is randomly being switched on by this device. Okay. And so, you will have random polarization state generation, and everything is being combined. Okay. Then for free space we are doing, so we combine using this beam splitter, and then we launch through free space optics, okay, mirrors and all those things, lenses. And suppose you want to have fiber, so instead of this whole optics, launching and collection optics, you can connect here fiber coupler, and you can connect here, okay, the receiving end, okay, receiver. So that becomes fiber. Although certain other things are involved, okay, when you are doing fiber, okay, we can discuss when we are going for fiber, okay, next lecture. So that is what arrangement. So and this laser diodes, if you notice, we have half wave plates, okay, we have half wave plates, you can see there, and this is half wave plate. And what is PBS? Anybody knows PBS? This is polarizing beam splitter. What it does, polarizing beam splitter? It transmits horizontally polarized and reflects vertically polarized. That is why polarizing beam splitter. So that is what it does, it transmits horizontally and reflects vertical. Okay. This direction is wrong, this PBS thing, it should be like this only, then only it will get reflected there. Okay. So anyway, so that you have to notice and tell me. So so this half wave plate and PBS combination earlier, so that is being used to attenuate your laser. Why? Most of the lasers, unless until you demand, they emit polarized light, okay, linearly polarized light, and if you put a linearly polarized light, and if you rotate another polarizer you put after that linearly polarized light, and you rotate, it will reduce the intensity of that light, okay, because projection in that direction only, so it will reduce the intensity. So that is what you are doing, you are using half a plate here, and this linearly polarized light is coming from laser, and you reduce the intensity, and then another half wave plate. Now PBS is making horizontal and vertical polarized light. So here another half wave plate, you this is linearly polarized light here, horizontally polarized. Another half wave plate, if you put at 22.5 degree, it will generate diagonally or anti-diagonal polarized. Okay. If it is vertical, it will generate anti-diagonal. If it is horizontal, it will generate diagonal. And same way here you see that here it is half a plate. So here it diagonal, anti-diagonal you are generating, and here it is being used for attenuation, and here only PBS is there. So this reflection will have vertical, and transmission will have horizontal. Okay. So now you have 4 polarization state, you combine using beam splitter, okay, and then you launch, and then you collect it, and here it is again beam splitter. So beam splitter, suppose you have single photon, weak current pass, but suppose you have single photon. So this random selection of basis is being done by beam splitter, it is passive random number, passive random selection it is doing, okay. Because if it is single photon, beam splitter we have discussed, either it will be reflected or transmitted. So random selection of basis is being done by that. So suppose photon is being transmitted, so here half wave plate is there, so it will generate the diagonal basis, okay, it is generating, selecting diagonal basis this arm, and here only PBS is there. So this reflection thing, this is selecting rectilinear basis, but this is being done randomly because you are using beam splitter, you are getting. So here we are using RNG, okay, to generate this randomly, but here we are using beam splitter for random selection of basis. That is the point one should note. So here we know, suppose this is like horizontal, so where it will go horizontal, where it will go vertical, we know here this will get like diagonal, this will get vertical, this will anti-diagonal, this we know this transmission thing horizontal, this vertical. So, this we know. Okay. So,
Not use SWP for the vertical line.
pardon,
In horizontal line at the receiver, we have used SWP.
here
Horizontal line.
here because PBS is there, and PBS what it does, it transmits horizontal and reflects vertical. Okay. Again here this is wrong, it should be like this, then only it will come to this direction. So, this will be horizontal, this will be vertical. Here 22.5 it is rotated. So, and this is like horizontal thing will make. So, this will be diagonal and this will be anti-diagonal. Okay. So, we know in which detector we are getting which polarization state of. Okay. Suppose horizontal, this will have get click. Suppose this is vertical, this will get click if vertical photon is coming. If it is diagonal, this will get click. If it is anti-diagonal, this will get. So, we know which detector. So, this is the arrangement. Okay. And so, once you have, then you can take it to the field. Okay. You can say these are called optical breadboards. You can see that these holes are there, M6 screws are there. This is optical breadboard. You make your setup on optical breadboard or your optical components, you fix on that, and you can take it to the field and you can do the experiment free space. So, that is what we have done this free space experiment, and this is 200 meter quantum key distribution. Okay. 200 meter quantum key distribution free space. Okay. And here non line of sight, not direct line of sight, you see that it is being reflected, then it is coming. Okay. Why we have made this kind of arrangement, you may ask, what is the logic, why not direct, just straight away we could have gone 200 meters, why we get this reflector we have put there. So, in our campus where our lab is there, we have only 2 buildings available which has line of sight available, and they are 100 meters apart. So, you may ask why you would have done 100 meters, why you wanted to do 200 meters, why you put reflector. But I got a project from DST. Okay. That project was free space quantum communication, road to satellite quantum communication. There I was supposed to show 200 meter quantum key distribution free space before I go for satellite. Somehow these experts, they put 200 meters, you have to show first phase, then you go for satellite, and this was only 100 meters. So, we put reflector, luckily it was 100 meters, it was not less. So, I put reflector and then we could get the light here, and these were the 2 chambers. So, these 2 chambers box. So, and then we can do 200 meters.
Can we put another reflector and make 300?
You can keep on, but any reflector there will be losses. You can keep on increasing distance. Okay. You have to have more infrastructure and losses will be also there. All reflectors will have some loss. Okay. Few percent, 2%, 4%, something like that. And if reflector is not good, that like your mode quality also degrades, and this collection efficiency becomes poor. Not only loss, reflection will have certain loss, but reflector introduce like degradation in the mode, and when you are collecting that light, if mode is not good, collection will be not good. Okay. When you are collecting that, when you are coupling through fiber and all those things, so there again you lose. So, that is what you do, that is why timing synchronization and timing is very important. Suppose this Alice as polarization is being detected at Bob site as polarization, Alice as anti-edge polarization. So, you get like this kind of, and this you notice that even if you up by 1 nanosecond or 2 nanosecond, you will not get this kind of count, you will get very less. Okay. This corresponds to around 200 meters. Okay. That is why you have this kind of, if you calculate the light speed, it will come around that. So, if you are having right state and right detection, it is going to right detector, you will get high counts and right timing. Okay. Now, if you see the counts in this vertical thing where this vertical photons are getting clicked, okay, detected, it will be very less because Alice H polarization is being there, and then timing same. Okay.
But at 72 we have a very
That is like okay, we will see, not very high. Okay.
that corresponds to some other basis.
Yeah. But what is important here, okay, you notice that now we are counting the H polarization of Alice, but Bob side we are taking the counts of detector which is supposed to detect diagonal polarized light. You see that it was 450 plus there when H was there and H was being observed, but now this D it is around 200 something, and same number will come in A also, because horizontally polarized right you can always write superposition of diagonal anti half of. So, again 200 plus something is coming for anti diagonal thing. Okay. So, means your system is fine, okay, it is working, your polarizer and everything, detector system, everything is fine, and then you can measure the key. Okay. So, that is how you do that, and for parameter estimation you do before you extract the key, because key rate formula will have need this information to extract the like to calculate the estimate the key, and so you have channel transmittivity, like transmittivity you know, and then mean photon number per pulse you have to know, you have to calculate, that is very important how you calculate the mean photon number per pulse. Suppose there are techniques to measure the mean photon number per pulse, and how accurately you measure mean photon number per pulse, because everything is based on that. That may lead to some problem, information leakage, that also you can calculate, but right now we are not going to discuss that. So, it is very important to calculate accurately this mean photon number per pulse, okay, estimation of that, and then you have to know the efficiency, and then repetition rate of laser, at what repetition rate you are generating the laser. If you know all these things, you can calculate the key rate, and then this shifted key rate, shift key rate, then you can have error correction, LDPC codes you can run, and then hash functions you can use for price simplifications, and then you get the secure key rate. Okay. And this is like quantum bit error rate. Okay. These are the error bits. Error bits means it was supposed to be H, but you are getting V. So, that is basically error. Okay. And then these are error bits, then you can calculate this quantum bit error rate, you know what is the like shifted key rate here, then you calculate, and what it is, it has to be less than 11.2%. Okay. We are doing BB84 protocol. BB84 protocol, if error rate is more than 11.2%, you will get 0 secure key. If you put the formula, okay, for secure key rate for BB84, if error becomes more than 11.2%, you get 0 secure key rate. So, it has to be always less than that, then only you get secure key.
Is that because Eve will be able to
Means you assume that whatever error is coming, some Eve is there. All the error, it may be atmosphere, anything. Okay. Any error is coming, it is coming because of Eve. Eve can take advantage of that. So, if error is more than that, okay, error is coming.
that value is calculated empirically, or like is there a proper theorem or formula for that?
Proper theorem, proper formula, it is not empirical. So, that is why this BB84, okay, is the theoretically proven, okay, theoretically proven secure protocol. There are other protocols which are not theoretical proof, are not there, but BB84 as you say is theoretically proven formula is there, okay, that calculates the thing. Others are not so
That 11% is
yeah, 11.2. So, this is like prepare and measure. So, same way you can have B92, here we have prepared 4 polation state, B92 you prepare 2 polation state, and then you again do random selections, are the basis, and then you develop the key rate. Key rate, because we are generating 2 polation state and sending, key rate will become half. Okay. So,
Call it 84 I have understood because 4 for the Nigeria.
pardon?
84 is the year.
1984. So, now we will go to entangled photon based protocols. I am okay, still there is 10-15 minutes, we can discuss 15 minutes, okay, not a problem. So, let us go to, like, that was prepare and measure protocol. Okay. BB84 protocol is the standard prepare and measure protocol, and variations are there. BB84 Decay-State protocol is there, and then we have developed our own protocol. I am not going to discuss that. Maybe Decay-State protocol we will discuss, because it came against this Decay-State protocol came to avoid some attacks which are very crucial attacks. To avoid, we will discuss Decay-State protocol when we discuss security and all those things, maybe next lecture. But right now let us see the entangled photon based protocols, how they do. So, here as discussed, this is second order nonlinear crystal. Okay. We have to have a non-centrosymmetric crystal for second harmonic, and then this pump pleasure is there. Okay. So, this is frequency, this is the wave vector, okay, momentum, okay, wave vector momentum you can say, and then this is second harmonic generation. So, like second order nonlinear crystal, so it generates 2 photons, okay, because of second. Suppose it is third, it will generate 3 photons, okay. That also one can do, but efficiency will be very poor. Okay. So, second order you generate this. This is named as signal idler. There are 2 photon pairs, one can be like, one is called signal and other is idler, and these are the wave vectors for that. So, this process, this nonlinear parametric, like spontaneous parametric down conversion, it conserves the energy and momentum. Okay. So, phase matching condition, basically this momentum conservation, you can see that momentum is conserved, this pump photon momentum and this. So, this is conserved. So, phase matching is momentum conservation, and this is energy conservation. So, it follows energy and momentum conservation, and that is how you get these paired photons. And then measuring the correlation, as I discussed in earlier slides, you can verify whether they are entangled, or using like detecting one photon, you can develop like single photon, Herald single photon. So, why I have written this references, like in India guys are there who are working, okay, and they have written good review articles on that, like Suman Karan, he is like PhD student with Anand Jha in IIT Kanpur. Ali is our student, although he shifted to NUS, then UK, but after going to NUS he wrote this review article along with project supervisor in NUS. So, these are the good review articles one can go through if you want to, for entangled photon source, and using bulk crystals. Okay. This review article, they talk of this entangled photon source using bulk crystals, but there are other methods also other than bulk crystals to generate entangled photons. So, this is one of the designs for generating entangled photons, okay, one of the setups. It is not like ultimate or this is the only setup, there are many designs, okay, for generating entangled photons. I do not know whether this slide is having or not those many designs, maybe some other slide might be having, I will have to open, but there are n number of designs you can use. Basically, you have to generate 2 photons and you have to measure correlation between these 2 photons for certain observable, for certain physical variable. So, here this uses Sagnac interferometer, okay. This is like this loop is called Sagnac interferometer, okay, because this same reflected light and transmitted light from this, they follow the same path. So, that is kind of thing is Sagnac, and then they do the interference. So, and this pump is there, this is called Sagnac interferometer based design. So, pump is 405, and then here let me go back slightly and tell you more information. So, here you see that. So, these two photons which are coming, they may be of different wavelength, okay, and they may be of same wavelength, okay. It is not compulsory, they will follow energy conservation, but they may be of different wavelength and okay, they may be of same wavelength. So, that is called degenerate. If they are having the same wavelength, it is called degenerate. If they are having different wavelength, it is called non-degenerate. Same way, these two photons may be coming like at certain angle, non-collinear, or they may be collinear. So, even if you do this, it can conserve the momentum. So, they can be collinear or non-collinear. So, all those things are there. Okay. And then there are processes like type 1, type 2 and type 0, okay, this down conversion. Type 1, what happens? Type 1, this polarization of this pump and polarization of these two photons, okay. These two photons type 1, they will have same polarization, but orthogonal to pump. Suppose pump is having horizontal polarization, and then these two photon will be have vertical polarization. Type 2, what happens? Okay. These two photons will have orthogonal polarization instead of same polarization, and type 0, both will have same polarization, pump as well as pump photon. So, you can have all the combinations, which kind of experiments you want to do, you can use that kind of down conversion. Type 0 will have same polarization, but it will be same as pump. In type 1, pump and this orthogonal, that is it. Type 0 you can't have in this kind of bulk crystal, you could have periodically poled crystal you should have, you can't have this. So, this crystal also, you can't have all type of conversion in the same, you will have to change the crystal design and cut. So, here this is pump is there 405, and we are doing degenerate entangled photons we are making, and polarization entangled, degenerate polarization entangled photons we are making. So, pump is going there, and then this is, you see, this is just like mode quality we are improving using lens and all those things, or efficiency of the process, okay, everything we have to take care of. A certain polarization state we are selecting, then collimating, and then it passes through the DPBS. You may ask PBS तो ठीक है भाई बता दिया कि reflect करता है, transmit horizontal, but what is DPBS? DPBS is dual polarizing insulator, okay. What is the meaning of dual? You see here there are two wavelengths involved, okay. One is down converted and degenerate. So, it is 810 and this is pump. So, there are two wavelengths involved, and this PBS works for both, okay. So, that is why dual, it works for two wavelengths. Same way it is dual half wave plate. So, this half wave plate also works for both the wavelengths, okay, and these are the mirrors, okay, and this is the nonlinear crystal. Now, instead of BBO it is periodically poled KTP crystal, and this oven. So, you have to keep at certain temperature. For this kind of down conversion, you have to maintain the temperature. If you change the temperature, down conversion phase matching condition will be different. It may become non-degenerate, it may become collinear or non-collinear depending on that. Okay. So, you have to maintain certain temperature, that is very critical, okay. And then this is type 0. In this experiment, you can have 2 also problem. So, you can have type 0 efficiency is higher compared to type 1 PPKTP. So, and then these two photons, okay, they are collected, fiber coupled, and they are being analyzed, okay, for their polarization correlation. This filter is very important, okay. This filter, what it does, it cuts out the background, okay. So, this is like plus minus 5 nanometer. So, you are generating 810. So, this will not allow any light to go to the detector, this filter. So, you put just before, this is a fiber collimator and then fiber coupled detector you are using to provide the background. So, these things are very important, coupling the detector, then fiber coupler, all those things, they are like parameters are very important, how good you are coupling, and then filter. Okay. So, once you collect that and then you do the coincidence. DPBS basically dual polarizing method. Dual means for two wavelengths it is working. In general, you have PBS, it works only for one wavelength, other wavelength it will not. So, it has been designed for both the wavelengths, it will work for both. So, that is the meaning of D here. So, now you have polarizers, you can rotate the polarizers, these analyzers, and then you can have like polarization correlation you can study. And these are the single photon detectors, single photon counting modules, and they are connected with timing electronics. Okay, that is not made, but they are connected with timing electronics, and that measures the coincidence count. Coincidence count you have to measure. Quantum mechanics, quantum mechanical measurement, most of them are like coincidence measurements. Okay, coincidence measurement basically heart of quantum measurement. So, that is what you do, and then suppose this analyzer angle is this and another, you fix this at certain angle, okay, this polarizer or analyzer whatever you call, and then you rotate the other one. So, you get this kind of coincidence counts. Okay. You are using two detectors, two photons are there, two detectors are there. So, this coincidence counts will vary. Okay. And okay, you have fixed one like this is horizontal, suppose you fix, and then you keep on rotating the other one, or if you put diagonal then you keep on rotating the other one. So, you get this kind of maxima minima, basically interference, okay, maxima minima. Okay. And these are interference pattern, you can measure the visibility. Okay. You can say what is interference here, this is two photon interference. Okay. And this is polarization correlation you are doing. Okay. What you do in interference experiment, you do field correlation. Okay. When you say interference and you see the visibility fringes, basically you are doing field correlation. That is why you see the interference fringes and you calculate the visibility, how good this visibility is there, contrast is there in interference. Here you are looking at polarization correlation, two photon, measuring photon, and again you see the visibility. Okay. So, using this visibility you can say ki how good like your entanglement is there, and then you can do the quantum state tomography. Okay. Quantum state tomography it does like tomography, how do you CT scan you do. So, you make number of measurements and then you combine to create the like your brain. Okay, map the same way you make number of measurement on the quantum state. Suppose we want to generate this quantum state. Okay. Yeah, bata. But for quantum state, not the process, you can have both the things, process tomography as well as state tomography. So, we are doing state tomography, we are making number of measurements on the generated state, this two photon state, okay, this entangled state. So, we are doing the, and this we want to generate. So, we make number of measurements on the these paired photons, and with that we can do the quantum state tomography. Okay, we can reconstruct the state, and you see that fidelity that measures how close you are there to the ideal state. So, you make experimental measurement, combine all the experimental measurements and then find out the how close you are to the desired state, and we are very close, 0.975, so 97.5. And this we have observed very robust, this entangled photon source, and we wanted to send as a payload, but although it does not materialize. Okay. But we can one can send this kind of entangled photon source for to the satellite and do the entanglement based quantum key distribution and all those things. Yeah. This is lab only, very compact we have made. Okay. It's not like it's our PLA design. Okay. we have made, we use it, and this kind of setup we use for entanglement quantum key distribution protocol in free space. So, not only that, you see that what happens if you go back, you are collecting this after this crystal, you are having non-collinear photons and you are coupling to the fiber. Okay. Now, suppose this angle between these two photons, okay, which are coming, that changes, okay, the cone becomes larger, okay, and angle may change depending on the temperature and other, like suppose your laser is having some fluctuation, there is temperature fluctuation in oven. So, all those external parameters may change the angle between these photons, okay. And this ring size, which is SPDC ring we call, if you record these two photons together on a EMCCD or CCD, okay, CMOS CCD, so you will get this kind of ring, okay, and this ring sizes changes, okay. You can see that ring sizes changes as we change the wavelength or crystal angle. Suppose crystal is not, this angle slightly changes. So, depending on crystal angle it will change, okay. Then temperature fluctuation is there, it will change. So, what one can do, one can use some optical arrangement, okay, so that your SPDC rings remain same, okay. So, we have used this optical arrangement, this is exicon and this is lens, combination of exicon, this is a particular optical element, this triangular thing, okay. So, and this lens combination, that will generate a perfect ring and this perfect ring will not change with change in the wavelength of photon, change length of a pump, okay, fluctuation in pump wavelength, it will not change. Same way crystal angle, suppose slightly deviated, it will not change. If this temperature fluctuation is there, you see it will not change, right. So, after this arrangement, this is before the arrangement, this optical arrangement, it will change, after this arrangement it will not change. So, your fiber coupling will be much more efficient, always you will be getting collecting same number of photons. If it is changed, this fiber couple, you know that fiber, this core diameter is few microns, if it changes you will not be able to couple photons to the fiber.
Crystal angle means is it a KDB crystal?
Yeah. There is some problem in the, like how it is, it is not normal incidence suppose completely. So, it will change.
So can be only KDB crystal?
One small interruption, Dr. Singh, this is also lunchtime.
150 na, I think.
Yes, it's exactly 1:50.
Okay.
So,
I will just complete.
perfect.
Yeah, just 5
Then
minutes.
can we, you can meet him at lunch or maybe after the program.
I will just finish in 5 minutes. Yeah, very close to. So, how do you verify that they are entangled? So, you measure the coincidence counts, that is what I am been telling, the coincidence measurements are basic to the quantum measurement. So, at different angles of these polarizers, there are two polarizers to measure the polarization of two photons. You measure the coincidences, these are the coincidence counts, okay. Using these coincidence counts, you can measure the correlation coefficients or correlation coefficient E alpha beta, and then once you can calculate this correlation coefficient, this is called Bell parameter. You can put this correlation coefficient values for different this polarizer and laser angles, and if this correlation this Bell parameter is more than 2, you can say that more than 2, it says that they are entangled, okay, and maximum value will be maximally entangled, it will be 2 root 2, close to 2 root 2. More than 2 it is entangled, okay, maximally entangled it will be close to, very close to 2 root 2. So, that is how you verify, using coincidence counts you can verify. Then you can use, once you have entangled photons, you can use for entanglements based QKD. Same thing BB84 only, but here is the preparing measure. You are sending these two photons and they are using selecting random basis. Same process goes, same basis, error correction, all those things are same as BB84. Similar, instead of preparing measure, again you have 2 photons, 2 stations, and then you do the measurement. Here you see that what has changed. Here this is entangled photons source, one is going to one party, one is going to another party, okay, and they make measurement, timing, electronics, everything remains same, launch and collection, everything similar, just 2 parties, they are getting 1 photon each of the pair and they are making measurements. Same way here you will see now Ellis and Bob. In other experiment BB84, Ellis and Bob were sitting in different room, different cabin, here they are sitting in the same cabin. You will see the effect what will happen here if you, and this is the detail arrangement again, okay, and this detail arrangement is there, reflector 200 meters. We have used one reflector here also, is the same building, this boundary wall, on that we have put reflector. So, we could study like how different distances are affecting the key rate and depending on atmospheric parameters, that also we studied. So, after this 200 meters we measured visibility as I explained earlier. For measuring the correlation you use that, and these are 98% confidence interval lines, okay. This is theoretical fit middle one, and then you measure this interference and then you calculate the Bell parameter, this interference curve coming out of coincidence counts, okay. So, using coincidence counts, this correlation coefficient, you can calculate this Bell parameter and visibility is pretty high. So, this is much more than 2, so they are entangled, and now they are entangled, you can use it for key distribution. And here what I wanted to tell you, because they are sitting in the same cabin now, Ellis and Bob, distance has changed. So, you can see that there it was 689, now it has become 648 nanosecond. So, timing is very critical even nanosecond, okay. So, again same temporal filtering you do, if H polarization state you are detecting Ellis side and Bob side H, so you will get maximum, okay, similar kind of thing. And then this diagonal thing will form the key, because you have generated HS plus PV state, and HS PV can be a DD plus A also you can write. So, this diagonal thing will form the key, and same parameters you have to know, okay. And then using coincidence detection you can, this is the key, and you can calculate the error rate and all those things, then error correction and privacy simplification you can do, and you can get secure key. So, you can study the effect of this atmosphere also, okay. This is mega meter inverse, not like typo error, this is mega meter inverse, okay, M is mega, and that is the atmospheric guys use. So, you can have like atmospheric parameter for that day or that time. Luckily in PRL we have atmospheric sciences division which keep on monitoring on a regular basis, hourly basis, these atmospheric conditions, okay. They have a machine on, and that gives this scattering. PM25 means particulate material less than 2.5 micron. So, microgram per meter cube. So, concentration of this aerosols and scattering coefficient, extinction coefficient, you know. Based on that you will see that if there are more aerosols, aerosol load is high, atmosphere is dirty, you get less key, and if it is higher you get if it is like atmospheric pollution is less, you will get higher key. Rainy season depending on wavelength which we are using, if it is very sensitive to atmospheric vapor and water vapor, water molecule, it will reduce, that is all. So, I will stop here, and then we can discuss rest next.
Thank you. So, we will probably not take questions now,
Mm-hmm.
and we will come back at 2 o'clock here.
बस थांबलेली आहे, बसने से जा करा,
that
चालत
will be
थोडा
better.
वेळ जाईल.
Okay, yes. So, there is a bus to take everybody
Mhm.
to the
Everybody will go by
cafe
bus.
and
Mm.
back.
Okay.
Okay, so kind of continuation of quantum mechanics that we had discussed, but more on quantum statistics. So, Professor Gangal has already talked about classical statistical mechanics. What is the difference is classical particles we say are distinguishable, whereas when we are going to quantum regime the particles are indistinguishable, and therefore there has to be a different statistics that we have to understand which these quantum particles will follow. So, I will just briefly repeat what Professor Gangal had done and then we will proceed. So, basically when we are talking about quantum particles, we the basic understanding is there will be probabilistic interpretations, there will be wave functions, we will have operators which will correspond to observables and things like that, and therefore we will have to do some kind of averaging, and there will be a concept like density matrix. I think Professor Zog, you have discussed density matrix or no? Okay, so there will be a concept of density matrix which which will be equivalent to the density function that Professor Gangal talked about. So, what he had told was that for a given macroscopic state, you can have different microscopic states, and a collection of these microscopic states is what we are interested in. And then he had talked about the thermodynamic limit where n tends to infinity, v tends to infinity, but the density remains constant, and then there are certain quantities like energy and entropy which we can talk about, which are related on these things. He had talked about postulates of equal a priori probability. That means for a given macro state you will be having many different micro states, and at any particular instant the probability of having any particular micro state is equal. So, it is the postulates of equal a priori probability. And then he had defined the entropy as k log omega, where omega is the number of microstates at a particular instant. Then he had discussed Hamiltonian's equations of motion, which we will not deal with, but he had defined what is called a density function. So, although I am writing q and p, this will be a set of all the coordinates q. So, if the density the degrees of freedom is say or there are 3n particles, then there will be corresponding 3n positions and the corresponding conjugate 3n momenta. So, depending on the degrees of freedom of the system, you will have those many q's and p's, and at a particular instant what you define is rho. So, basically what we are saying is for a classical system you are working in a phase space, and the state of a system is defined as a point in this phase space, and then we are talking about all the possible states in the phase space, and rho defines actually the density of the points in the phase space. So, it describes the manner in which the members of the, so he also talked about ensemble. So, we have a, now we are not dealing, as we were discussing in quantum mechanics, we were always saying that we are talking about one single particle, but here when we are talking about statistics, we are actually dealing with a large number of similar particles. So, we are talking about an ensemble. And then he had also discussed microcanonical ensemble, canonical ensemble. So, in microcanonical ensemble what we have is the number of particles is fixed, the volume is fixed, and the energy lies between some E and E plus delta E. Whereas in canonical ensemble what we assume is the system under consideration is in contact with a heat bath, and therefore the temperature, it can exchange energy with the heat bath, but the temperature is constant. And therefore, this is, as I said, is the distribution or the way the different microstates are distributed in phase space. And then from this he had discussed what he denoted as the ensemble average of some quantity which depends on q and p. So, we will will have a quantum analog of this density function, which will be a density matrix. We will talk about that. So, this is just a revision of what he had discussed in his lecture. Now, we will go to why we are going to quantum statistics, or why we are going to discuss something different than what he has discussed. So, we are now talking about a system where we have indistinguishable particles. So, in Maxwell-Boltzmann distributions or in classical physics, you can say that particle A and particle B, and if you interchange them, then you know that this is a different situation. But when you are talking about electrons in a solid or similar entities which are identical particles, if you interchange two electrons, you are not going to see any difference in the system. So, the statistics which deals with particles of which are indistinguishable or identical, that is called quantum statistics. And the thing is, there are only two possible distributions that you can have for such particles. So, for example, if I have two particles and I denote by psi the wave function of these two particles, and I have some operator, let me call it some p, which is equivalent to saying that this will interchange the two particles, coordinates of two particles. So, p operating on psi 1 2 gives me psi 2 1. So, basically this is a operator. Yeah. Yeah. So, basically whatever the particles, the states in which they were, that state so particle 1 was suppose in a state A and particle 2 was in some state B. Now, we are saying particle 2 is in state A and particle 1 is in state B. Okay. So, now again if you operate on this, that means you say psi 2 1, that means these will be interchanged. So, this will become psi 1 2. But if you go back to the definition of psi 2 1 here, this is equivalent to saying that if you operate by this operator twice, you are going to get back the same wave function. So, what does this mean? This means that whatever this operator is doing, the corresponding eigenvalue is such that its modulus is 1. Yeah. So, what can be the possibilities? This can be plus 1, this can be minus 1, or in general it can be e to the power I theta type. We will be discussing only about these two, when this is plus and when this is minus. This is a situation which occurs only in two dimensional systems, and those are anyonic systems, so we will not deal with them. So, when we say that this is the case, that means what we are saying is psi 1 2 is same as psi 2 1. That means when I interchange the two particles, the wave function does not change. You call this as a symmetric wave function, and the particles which obey this rule, they are called bosons, and they obey what is known as the Bose-Einstein statistics. And the particles for which when you interchange the two particles in some states, if the wave function changes sign, you say the wave function is antisymmetric under interchange of two particles, and those particles are fermions and they obey Fermi-Dirac statistics. Okay. So, from this point onwards, we will now go to quantum mechanical systems. But before that, I would like to do some mathematics which is parallel to what Professor Gangal had done for classical particles. So, as we know, we are talking about quantum particles. These will obey the time dependent Schrodinger equation and so on. So, we are going to assume that, and then what I am saying is, suppose I have a psi which is a function of all these q, p and, or in general q and t, not p, because you know in quantum mechanics you can't define the position and momenta simultaneously. So, this will be a function of coordinates of all the coordinates or whatever properties, like there can be spin also. So, q actually is a quantity which denotes everything about the particle and time. So, if I can suppose phi and t, they form a basis, then you can expand this wave function as C n t phi n q t. So, phi n's form a basis for this space. Normal possibilities which we had already discussed earlier is summation over all n is equal to 1. Only thing is now there is a time dependence here because we are talking about dynamical systems. And then expectation value of any observable for which we have the corresponding operator f will be defined as psi star q t f operating on psi q t dq. And if you substitute this, then you will get and this I denote as f n m. This is so corresponding to this observable you will have a matrix and this is one particular element of that matrix. So, you will have this as summation C n star t C m t f n m sum over n n m. So, this averaging is because of the probabilistic nature of the quantum mechanics. Okay. Then there is another thing, we are talking about an ensemble of systems. So, let us say that this is for a particular system, say alpha. So, I will call this as, so I am taking one particular system of this ensemble and for that I am calculating this expectation value of an operator. Then for the whole ensemble I will have to, that I denote by this quantity, this will be, if the totally is suppose there are n number of systems, then alpha goes from 1 to n. So, you have two kind of averaging here. One is because of the probabilistic nature of the quantum systems and other is because we are talking about a large number of particles or large number of systems that comprise our total system. So, you have two kinds of averaging, one is ensemble. So, this is called ensemble average and this is normally the whatever expectation value as we have defined in quantum mechanics. So, when you are doing this averaging, automatically when you have this averaging here, this will be sum over n, sum over alpha going from 1 to n. So, correspondingly your Cn's will also be dependent on alpha because now I am saying f alpha in so that particular system. So, that these Cn's become dependent on alpha. So, I can write Cn star alpha t Cm alpha t average of this is equal to 1 upon n summation alpha going from 1, I am summing over alpha. So, these will not be dependent on alpha. And this is what I call as rho n m. Okay. So, this rho forms what is known as the density matrix. It is similar to the density function which we had for the classical system.
What will be the dimensions of this n cross n?
Yeah. And the diagonal element will be rho n n will be mod of C n t square. And this will represent, as we know, the probability of finding the system in a particular state phi n, as we had earlier interpreted this, mod Cn square tells you the probability of finding the system in the state phi n. And using this density matrix you can also then define expectation value as so f nm is this particular element and divided by this, assuming that. So, this will be actually trace of rho f. So, you will have a matrix which is corresponding to these elements, they will form a matrix for corresponding to the operator rho, and f is the operator corresponding to a specific observable. Trace of this is what gives you the expectation value. So, this is similar to what you have done in classical mechanics, and we also have similarly a quantum analog of the Liouville's theorem. I am not going to do the mathematics, but basically what you see here is this rho nm is dependent on time. So, you can talk about the time variation of this. So, if I talk about the rate of change of this turns out to be equal to 1 upon I h cross h rho, where h is the Hamiltonian for which these are the eigenstates. So, if a system is in equilibrium, then this is not dependent on time. So, this is equal to 0. So, that would mean either the density matrix is a constant or it is a function of some constant of motion of the system, or equivalently it says that the Hamiltonian and the density matrix they commute, and therefore, these will have simultaneous eigenfunctions. So, the eigenfunctions of H they also form the eigenfunctions of the matrix rho or the operator rho. So, this is the quantum analog of Liouville's theorem in classical mechanics, classical statistical mechanics. And you can also define this in terms of Bra and Ket as, so rho operator you can say is equivalent to saying phi Ket phi n rho n Bra phi n. All of you are with me? Any difficulty? Okay, so only some more mathematics, then we are through. I am not going to do much of mathematics. So, what we have said is corresponding to the density distribution in classical statistical mechanics, you have a density matrix here, and yeah, a few more things I want to. I am just checking whether I have missed any point to be told. Okay, so we have a corresponding density matrix, and that also satisfies the corresponding Liouville's theorem. Now, if we Again here also we can talk about microcanonical ensemble, canonical ensemble and also grand canonical ensemble. So as I said, microcanonical ensemble is where your n, v are fixed and energy lies between some E and E plus delta E. So you can say that, and omega E is the total number of accessible states for a system. Then what we can say for the density matrix is rho mn is equal to rho 0 delta mn for states whose energy lies, so epsilon I is the corresponding, suppose epsilon s is the energy, it lies between E and E plus delta E. So all those states for which the energy lies between this, they have a corresponding density matrix element like this, and it is 0 otherwise. And if omega E happens to be equal to 1, that will correspond to entropy 0. That means the system is in perfect order.
Each element or nm element of this matrix, density matrix, provides some type of correlation.
Yes. Only along the diagonal you get the probability, but otherwise it has a, it is basically it will be combining n systems in the nth state and the mth state.
Nth state and mth state means two different states.
Yeah, yes. The states which are forming a complete basis set for the system. So there can be only one particular such state where everything is perfectly ordered, and that is the lowest energy state. And if omega is greater than 1, then it will correspond to some larger value of S, and that would be a system. So when you have this condition, in that situation rho square is equal to rho, and you say that the system, these are actually pure states, and when omega is greater than 1,
Why will pure state satisfy this? Rho square is equal to rho.
that is what actually Zog sir has also discussed. Na? Can you comment on this? Density matrix, it has to be idempotent. Na? Yeah, yeah.
I mean, since you can write it in tensor form, so from there.
Yeah. That is how I had written. No? Oh, I have rubbed it. It is actually projecting out the system, no? Phi n operating on that. So basically what in general we say phi n, this is the projection operator, and when I had written with rho, so when we have rho omega greater than 1, that will be that the system is not in perfect order, and then it will be in a mixed state.
So if rho square is not equal to rho, it is in mixed state.
Yeah. Then we have canonical ensemble where you have n and v fixed, but energy is not. So the system is in contact with a heat bath. Its temperature is constant, but it can exchange energy with the heat bath. So E is a variable quantity in this system. And then the probability Pn that the system has energy En, this probability is proportional to e to the power minus beta En. Beta is 1 upon kT.
This is called sub.
Canonical ensemble. This was microcanonical ensemble.
So here we don't have any such relation that probability is
No, here we have said that the probability is 1 for all states for which energy is this, and for others the probability is 0. So, here energy is a variable and the probability of finding the particle in a particular probability of finding a system with energy E n is proportional to e to the power minus beta E n. Yeah. And then you define rho n as e to the power minus beta E n upon summation e to the power minus beta E n over all n, and this is what we call as the partition function.
Is there any rule of defining this or
Defining what?
you are defining rho n, right? This rho n we have to
Yeah. So, it is proportional to the probability. No? From that it will, because what we have said is mod C n square is the probability of finding the particle. So, density is actually, it is a kind of operator projecting out the particular state from that system. And the corresponding operator I can define as and similarly you can define average value of an operator. And the third ensemble that we talk about normally is grand canonical ensemble, where the number of particles in the system is not constant. See, normally whenever we are dealing with systems like system of electrons, say electrons in a solid, then the number of electrons is fixed unless it is exchanging electrons with somebody else. But here when we are talking about grand canonical ensemble, this is particularly important when we are talking about a system of photons. You know that if in a container you have photons, then it can absorb or emit photon without additional energy. So, to add a photon to any particular system, it does not require an energy. So, what we say is the corresponding chemical potential for a photon is 0. Okay. So, we will talk about that, but just here I will just define corresponding quantities for a grand canonical ensemble. You would say rho is 1 upon, this is curly z, which is again a partition function for this system. And likewise you can, as we had here average value of G, here similarly you can define in terms of this Z now. So, these are the 3 different ensembles that we consider in statistical mechanics. Microcanonical ensemble where energy is almost constant, number of particles and the volume is fixed. Canonical ensemble where the system can exchange energy with a heat bath so that its temperature is constant, and grand canonical ensemble where the number of particles is also not fixed, and that is particular the case when you are describing photons. So, I think that much of mathematics I am not going to do much of more than this. So, now let me talk about the concept of chemical potential. Do you all know what is chemical potential? Normally we talk about potential energy in mechanical systems, like if you have a ball and you throw it, it is at higher potential energy here, and when it goes down it has lower potential. Or you talk about electrostatic potential, and because of that charges flow So, similarly, so let us consider that you have suppose a bottle of some perfume. Normally the perfume is in the bottle, you can't smell it, but the moment you open the bottle you see that smell actually it spreads in some portion of the room. So, what happens? The perfume particles are diffusing in the medium. So, what happens is there is something called, so there is a tendency to go from one place to other. In a mechanical system we say potential energy is more, it goes to it tries to go to a lower potential energy, or in electrical thing you say that from higher electrostatic potential to lower electrostatic potential. So, here what we are saying that the molecules have some tendency to go from a region, or you can also compare, for example, if there are two rooms, in one room there are 100 people and the room is closed, and in the other room there are 10 people, and suppose there is a door in between and you open the door, what will happen? People will try to go from this room to that room because they do not want to be congested in a room. So, something like a tendency to go from a region where there is more pressure, you can say, and go to a less thing. So, this tendency to go from higher potential to a lower potential for molecules is what is known as chemical potential, generally referring to that. But actually mathematically we say that if you to a system you want to add a particle, to add that particle whatever energy is required, that is defined as the chemical potential. Okay. So, I have a system of say electrons and I have to add one more electron to the system, whatever energy I will require, that will be the chemical potential for electron of that system. It will depend on the temperature and the density, and whether there are interaction between the systems in that particular system or not. Okay. So, all this will decide what is the chemical potential. Actually that is why the air normally say when we breathe, in our lung there are air molecules and they go out to the blood. So, you can say chemical potential in the lungs is higher and in the blood it is lower. So, oxygen molecules try to go from the lungs to the blood where there is less oxygen. So, something like that. Analogies are not very good, but just to explain. But mathematically it is the energy to add a particle, energy required to add a particle to a system. There may be interactions between the particles, there may not be interactions in the system. Okay, so with this much mathematical background, let us now talk about the particles that we are interested in and why we are interested in these particles. Because the particles which actually form the qubits in your quantum computers, they obey these statistics. So, therefore, we have to understand the statistics and we have to know more about it. So, I will just write down, this is say quantum hardware, and the corresponding relevant statistics. So, you can have superconducting qubits, why this happens? This happens because of the, so each of these we will discuss separately. Superconductivity happens because of Cooper pair of electrons. We all know that electrons are fermions, but when two electrons come together, they form a Cooper pair which acts like a boson. More of it we will discuss. Then you have semiconductor spin qubits. So, here you have electrons which are fermions. Then you can have quantum dots. Which are fermions. You can have neutral atoms. These can be both depending on which atom you are considering. They can be bosonic or fermionic. This also I will talk about slightly later. And you can have trapped ions. So, they actually represent collective quantum states. So, typically I just wanted to say why we should study quantum statistics is quantum computers are built on underlying physics. Okay.
So if someone says we are using superconducting based quantum computer, then the underlying physics will be based on Cooper pairs.
Yeah. So what are Cooper pairs? Typically we know that electrons are fermions, and again I have not talked about spins, but basically this quantum statistics is one which connects spin with the statistics. Spin of the particle is connected with the statistics. So spin,
Only spin or the property?
no spin, spin. So if you have half integral spin, that is half 1 by 2, 3 by 2, 5 by 2, then those are fermions, and they obey what is known as Fermi-Dirac statistics. And if you have integral spin, that is spin is 0, 1, 2, 3, those are called bosons, and they obey what is known as the Bose-Einstein statistics. Okay. So half integral spin, fermions, and Dirac statistics, and integral spin are bosons, and they obey Bose-Einstein statistics. So what is a Cooper pair? So electrons are fermions. Electrons have half integral spin, each it's half. Okay, single electron has a spin which is half. Okay, here also I just wanted to emphasize that although we call it spin, there is nothing which is rotating here. Okay. So since initially physicists thought that because whatever the property it describes, it is corresponding, the dimensions are corresponding to angular momentum, and initially it was thought that something is revolving or rotating or spinning, and therefore you are having this property. So initial name given was spin, but then later on it was found that the angular momentum associated with the electron, if you really have to say that something is rotating and that spin value has to be there, then it would mean that you are having or rotating something at speed which is greater than the velocity of light, which is not possible. So then it was said that, of course people understood and then accepted that spin is an intrinsic quantity of the electron, something like charge or mass. We do not say that why of course there are explanations like Higgs bosons and all that, why there is mass for each entity, but generally in our normal situation we do not ask why this is so massive or why this mass is there or why an electron has this charge. So similarly we can say spin is an intrinsic quantity which we do not doubt, but it has dimensions of angular momentum. So a mass, charge and spin define the properties of an electron. So it is an inherent property of the electron. Just because initially the spin word was used, it continues to be used in, but there is nothing rotating in electron. It is an intrinsic property. So you have, if you talk about two electrons coming together, we also note that electrons have negative charge. So if two electrons are coming together, they should repel each other. They should not come together and form some kind of a bound state. that is our normal understanding. So, why then you get a Cooper pair, and that also why not in every material? You see only certain materials are superconducting. That understanding of superconductivity came from the BCS theory, Bardeen-Cooper and Schiffer theory, and there are other things also, like now people are also talking about other theories which explain high temperature superconductivity. We will not go into all that, but very hand waving explanation of Cooper pair I will try to give here. So, most of these analogies I am taking from ChatGPT, okay, not my own things everywhere. So, what they have described is, suppose you have a mattress of sponge and one person stands at a particular place, what happens? So that goes down, and if some other person is also standing, automatically it comes there, okay. So that there is no attraction in the two of them, or there is no repulsion also, there is no interaction at all between the two persons, but just because there was a what I should say slope in that direction, the other person also gets attracted. So what happens in the materials, we know that you have basically all the materials are made up of atoms. So you have positively charged ions and some electrons, not all the electrons. If you take any particular material, say sodium, it has 11 electrons, okay. Out of these electrons, so this is how the electrons are filled. These 10 electrons are more or less tightly bound to the nucleus. So the nuclear charge, that is plus electron protons, whatever neutrons are there inside the nucleus, and these 10 electrons, they form what is known as a sodium ion with one positive charge. So this will be Na plus, and then this electrons, it does not remain bound to that atom, it becomes a part of the whole atom, whole solid, okay. So these electrons are actually moving in the field of these positively charged ions, and in some materials, this does not happen in all the materials, in some materials there is some interaction between these positively charged ions and the electron, which tries to attract another electron to that place, okay. And actually it is not even the place, the two electrons can be very far apart, they need not be together, but there is some kind of attraction which is coming. I am not going into all the details, but this kind of attraction is coming because of the positively charged ions that are distributed in the solid, and therefore the second electron cannot move independent of this electron. So there is some correlation between the motion of the two electrons, they may not be actually bound, means they अगदी जवळ असे एकमेकांच्या जवळच असेल पाहिजे असं नाही, हां, you can say entangled, you can say. So there is some correlation between their motion, if this moves then automatically the second moves. So two such electrons which are bound because of the interaction of the lattice, they form what is known as a Cooper pair. And since there are two electrons, both of them,
Electrons are free electrons.
no, they are in the solid, no? They are
atoms are
atoms are बाहेर, but they are in the solid. So they are part of a solid. So these two electrons therefore formed what is called a pair, and that is called a Cooper pair. And the other thing is, normally when an electron moves in a, for example, even in a wire, we say that if you take the best, say gold or silver, still there is some resistance to the motion of the electrons. Why? Because the electrons interact, they are scattered by the ions. Some kind of resistance is always there. We do not see any resistance where total resistance of the electricals, like there is no electrical resistance, that does not happen, because there are some things which can scatter the electrons, and therefore the normal flow of electrons is interrupted. But that does not happen for these Cooper pairs, and therefore in superconductors you do not see, or you say superconductors are the materials where you have zero resistivity or zero resistance to the motion of the electrons, okay. So basically here what we are saying is, because of the two electrons you form a pair, and the electrons can be, okay, we have not yet discussed that, but basically there is Pauli's exclusion principle which does not allow two fermions to be in the same state. So, what do we mean by the state? So, let me go again to the case of atoms for example.
These are bosons.
Cooper pairs are bosons. No, I am coming back to Pauli's exclusion principle. Why? Like normally two things I said, that since they are negatively charged particles, they should repel each other, but they are somehow correlated because of the lattice interaction. Secondly, they are the two electrons are fermions. Okay. So, the Pauli's exclusion principle states that no two fermions can be in the same state. So, what do we mean by a state? So, for example, in an atom, that day I think slightly I had discussed, but not. So, particle in a box, for example, we had said that En is equal to n square pi square h cross square upon 2 ml square. So, this n was the state, energy state. Similarly, for a electron in, for example, a hydrogen atom, we say that E depends on E and n and L. N is the principal quantum number, L is the orbital angular momentum quantum number. And then there are other quantum numbers which, so psi actually corresponding the wave function will depend on N, L, ML and MS. So, these 4 are the quantum numbers which define the state of the electron in an atom. So, if all these 4 quantities are same for an electron, those 2 electrons cannot be at the same place. Okay. Or if N, L and ML are same, MS has to be different. So, you can say electron is either in the up state or in the down state. So, that is what is happening in a Cooper pair. You are having 2 electrons, but they cannot be in the, they cannot be both having up spin or down spin. Again one more, as we said that nothing is spinning, nothing is rotating. I would also like to talk about up state and down state. When we say up, it does not mean that something like up and down. It in general the spin can be oriented anyway. So, spin actually represents a corresponding angular momentum. It actually has a well defined thing when you apply a magnetic field. So, in a particular direction you are applying a magnetic field and the electron gets say along the direction of the magnetic field, then you call it an up spin electrons, and in the opposite direction then you call it a down spin electron. Okay. So, it has nothing to do with the general orientation, it is the orientation of the electron along the direction of the magnetic field, then you say up and down or parallel and anti-parallel. Okay, the other thing why you should study quantum statistics is the quantum simulations or quantum algorithms that you work with. Particularly simulations that are done on quantum computers are for say many body systems, are many electron gases or magnetic materials, superconductors, ultra cold atoms. All these can be understood only if you understand the underlying statistics. And why it is called statistics? It has nothing to do with data analysis in some sense. Like normally when we say statistics, we call about, like we try to call talk about mean, mode and median and all those things. So, statistics is because large number of particles are involved and you are taking an ensemble average of that. And then when you are dealing with quantum computers, you have to understand why superconducting circuits work or how electrons occupy the quantum states in a semiconductor, because semiconductor materials are inherent part of a quantum computer. Why quantum processors have to work at cryogenic temperatures, and how many body quantum systems can be simulated on these quantum systems. All this if you have to do, you have to understand the corresponding quantum statistics. And this is all what is involved in quantum computing. So, physical realization of quantum computers is not possible unless you understand So, those who are just using them need not understand, but those who are building them, they should understand the corresponding quantum statistics. Huh? Yeah. Yes, yes.
I mean, if the problems are in
Yes.
body theory,
Yeah. Okay, so now what I thought is, particularly since you will be teaching more or less the computer science students, that is what I understand, or in general all engineering students or what? All engineering students. Okay. So I thought that some analogy with computers if we can give. So if you are writing suppose an algorithm or not algorithm actually, you are writing a software to allocate, scheduling is to be done, for example. You have some tasks and they are to be distributed on different processors. So it does not matter how the processor, which processor are fast or, but basically what are the resources available and how these tasks should be distributed on these resources available to you. So something similar to that when we do in physics, we call it quantum statistics. And you can say it is a bridge between quantum mechanics and quantum computers. So basically you can give an analogy with resource allocation. So if you are designing a computing platform, cloud computing platform, and you have to assign the task, what you are talking about is what are the available number of servers, what is the memory available, what is the CPU capacity, what is the scheduling policy, and whether multiple tasks can be done on one server. So basically here this is your resource. The tasks that you have to distribute, those you can say are the objects that you want to distribute, and the scheduling policy is the rule by which this distribution will be done. So if you try to see a corresponding thing in a physical system, you can say that your energy states that are available are the resources.
Also require that task, what properties they have, we might have to specify.
Yes.
Like it might have the starting time, the deadline and things like that.
All that is I am not talking about. Basically I am just trying to see how you will schedule or how you will distribute the things.
Yeah, but
All that will be taken care of in the scheduling policy.
okay, are they real time systems? I mean, do they have some kind of deadlines before which they need to?
No, no, no. And the rules here that you will talk about are the rules that the particles obey. And your objects, that is the tasks, are similar to the particles that you have. So our quantum statistics tells us how these particles will be distributed in different energy states according to the laws of nature. And that laws of nature, as I said, they connect the spin to the statistics that they obey. So half integral particles will be fermions and they will obey Fermi-Dirac statistics. Integral spin particles will be bosons, they will follow the Bose-Einstein set. So what the statistics actually tells you? The occupation number for each state, that is what is important. And here I have taken a simple, I do not know whether you will appreciate this or not, but one example. I have 3 students, let me call them Ramesh, Suresh and Devesh suppose. Okay. and as a teacher I have to give 2 awards between 3 of them. Now these awards can be anything. So suppose initially I say that I want to give them some kind of a memorial coin or something, on which on one of them I have Newton's emblem and on the other I have Shakespeare. So let me call them N and S. So 2 coins, on one of them Newton's figure is there, on the other one Shakespeare. So they are distinguishable basically. These two, I have these 2 coins I have to distribute between these 3. I can decide to give both to this person and nothing to these 2, both to this person, nothing to these 2, or both to this person and nothing to these 2. Is one way I can do. Other way is and third way is so there are total 9 different ways in which I can distribute these 2 coins in 3 persons, to the 3 persons. So there are 9 ways of distributing. Now suppose I say that my award is not a coin like this, but a 500 rupee note. That means I want to give 500 rupees to the 2 persons. So then how I can distribute? I can give 2 notes here, nothing here, similar to this. Both the notes to only one person, nothing to others. The next thing is important, I give 1 note to him and nothing here. If I interchange these notes, it is not going to make any difference. It is going to give me the same configuration, I should say. Okay? So one possibility is this, another possibility is this, and third possibility is this. So there are only 6 ways to distribute these 2 things. Now what was the difference between this and this? Here the 2 things that I wanted to distribute were distinguishable. Here the 2 things that I wanted to distribute are indistinguishable, they are identical. So whether I give 2 to one person or 1 and 1 to, so basically whether I give 1 to this and then interchange them, that does not give me a different possible combination. Okay? And the third possibility is, as a reward I want to include one of them in a football team. So there are 2 vacancies in the football team and I want to accommodate these 3 persons. How I can do that? I can include these 2, I cannot include these 2, or so a person can be either included in the team or not included in the team. Okay, there is no other possibility. So there are only 3 possible combinations. So what I have done, I have 2 rewards given to 3 persons, but depending on what the reward was, the distribution was different. So similarly, when we are talking about the statistics, we are talking about the statistics that these particles obey. If they are distinguishable particles, then the distribution will be like this, which is the Maxwell-Boltzmann distribution. Because the particles are distinguishable, so when you change the particles, it is a different state. When the particles were identical, but there was a possibility that in a particular way or in a particular state both these particles can be accommodated. Like here I said I can give both the notes to one person. So it is possible to do that. These are what is the behavior like bosons and they follow what is Bose-Einstein statistics. and the third is each state is occupied by only one or not occupied. That is done by fermions, half integral spin particles, and they obey Fermi-Dirac statistic. So, the basic difference is, so we will not talk much about Maxwell-Boltzmann distribution because this is particles which are distinguishable. Now we are talking only about particles which are identical particles, because when we are dealing with quantum systems, we are dealing with electrons and things like that, photons, electrons, which are indistinguishable particles. So, we are only interested in Fermi-Dirac statistics and Bose-Einstein statistics, and as I said, it is related, this statistics is related to their corresponding spin. I am only going to give you the, so okay. So, here if I try to find out ratio if I say R is the ratio that the probability of two particles in the same state divided by probability of finding the particles in different states. So, this R for Maxwell-Boltzmann distribution will be what? Two particles in the same state is 1, 2 and 3, and 6 distributions are such when the particles are in different states. Okay. So, 3 states divided by 6 states, so this is half. If I want to calculate this ratio for bosons, we had total 6 states. In 3 of them the particles were in the same states, in 3 of them the particles were in different states. So, it is 3 by 3. So, this ratio was 1. And for Fermi-Dirac statistics, the particles in the same state, no. So, this is 0. So, what this tells you that for bosons there is a possibility or there is a tendency to crowd in one particular state, and this is what is used in quantum computing many of the time. So, the quantum computers which are based on bosons, they have this tendency that they try to come together. Okay, then I will just describe what is known as the occupation number and how it depends on the energy. Here what we have seen is, in Maxwell-Boltzmann anyway, we have 3 states in which the particles were in the same state and 6 distributions where they were in different states. So, the ratio is half. Here 3 in which the particles were together and 3 in which the particles were not together. So, this is 1, and here there was no state in which the 2 particles were together. So, the possibility of finding 2 particles in the same state is 0 for fermions, whereas for bosons it is actually more than that for the distinguishable particles, and this tendency actually tries to bring bosons together in the lowest possible energy state. We will talk about it slightly later, more about it. Okay, I will just give the corresponding, I am not going to derive the expressions, but I am just going to give you the numbers. So, you have a system S is the state of the system as a whole and small s is the micro state. So, maybe one system in the ensemble. So, small s denotes the one system, or for example you have a electron gas ideal or a photon gas, then single photon you describe by state S and the whole system you describe by capital S. Then I am denoting by Ns the occupancy of the S state or the occupation number, average number of particles in the state S. This is given as n e to the power minus beta epsilon S upon summation e to the power minus beta epsilon S for Maxwell-Boltzmann distribution. So, for the state S the corresponding energy is epsilon S. So, the average number of particles in this state S is given by this quantity. Beta, as I said, is 1 upon k beta t. For the bosons you have and what you have is total energy of the system is summation n ns epsilon s or even ns you can say over all s, and summation ns is equal to n. So, total number of particles is fixed. In this case you will see that epsilon s has to be greater than mu, because if it is not greater than mu this will mean negative values. The negative values for occupation number does not have any meaning. So, this is the primary condition, that energy of each single state is greater than the corresponding chemical potential. Only for photons what happens is mu is equal to 0, because you do not need any energy to add a photon to a system. So, this becomes 0. So, the distribution for photons is just e to the power beta epsilon s minus 1. And in that case this condition is not satisfied, because the number of photons in the system is not fixed. And the formula for the Fermi-Dirac distribution Ns is given as 1 upon e to the power beta epsilon s minus mu plus 1. Here if epsilon is very large, then this quantity will be very large and the average occupancy will be almost 0. If epsilon s is not large, but still it is 1 plus something. So, this denominator is always going to be greater than 1. So, the occupancy is always going to be less than or at most equal to 1. Okay. So, therefore, for Fermi-Dirac systems you will always have this less than equal to 1 or sometimes it is 0. So, that is actually what we were saying, that each state can be occupied only by, for example, I told about electrons.
It will be 0.
Huh?
And it will be 0.
It will be 0 when this quantity is large. So, very large. So, this will depend on the temperatures.
Can approach 0.
We will talk about that distribution also. So, here what we are saying is Fermi-Dirac statistics says you cannot have 2 electrons in the same state, or for that matter any 2 fermions in the same state, and that is exactly what is Pauli's exclusion principle statement is. You cannot have the occupancy of any state cannot be greater than 1. So, if we try to plot this function Fermi-Dirac distribution, suppose I have here this average Ns as a function of epsilon s. At t equal to 0, beta is 1 upon k beta t. So, if t is equal to 0, this will be infinity. So, this will diverge. So, occupancy will be 0. So, you get what is actually Fermi-Dirac distribution. Here this is equal to 1 and beyond this it is equal to 0 at t equal to 0.
T is absolute temperature.
Yeah. Okay. So, you will have states which are filled up to a certain energy and beyond that the states will be empty, and this highest occupied energy level is defined as the Fermi level. And as the temperature increases, this distribution slightly changes, it becomes like this. So, this will correspond to say T1 and this will correspond to T2, no sorry T2. So, as temperature increases, there will be deviations in some region, very small region around this. I have drawn this on a large scale, but only in some region around this point there will be a distribution change from the step function, but it will always pass through this point which is half. As the temperature increases, you will go more and more away from the ideal distribution.
So, most of the states will have 1.
Yeah.
Is this property useful for quantum?
Yes. That is why you have all this distribution, like why certain materials are metals, certain materials are semiconductors, certain materials are insulator. That is because of this, because the electrons obey Fermi-Dirac statistics. Because of that these properties are decided. Because we normally talk about the electronic states of electrons in a solid, and then if there is highest occupied level and lowest unoccupied level, there is a gap between them. If that gap is of the order of few electron volts, say 1 to say 3 or something like that, then you call it a semiconductor. If it is more than that, you call it an insulator, and if the bands overlap, then you call it a metal. So, all these properties of materials are decided are because of this Fermi-Dirac statistics the electrons obey. Okay, so there are other analogies which I think I am not going into details more of it. What remains is talking about any questions till this point. So, most of whatever was included in the syllabus I have covered. What remains is the Bose-Einstein condensation. Other things are discussed. So, do you have any difficulties? Okay, so then let us talk about Bose-Einstein condensation. See, most of the quantum computers that we talk about, they work at very low temperatures in nano kelvins or something like that, cryogenic temperatures. So, temperature has to, yeah. So, there I said that I did not write any of those statistics there, it was something different.
Those 3 is not the exhaustive set.
Which 3?
So, this is not the exhaustive set.
This is.
Okay, this is.
So, distinguishable particles Maxwell-Born distribution, and indistinguishable particles only 2, fermions or bosons. That is the most important thing.
Collective quantum states.
Yeah. And as I said, in 2 dimensions you do talk about something which are called anyons, but we will not go into those details. Because of that you see quantum Hall effect and things like that we will not discuss. But that is only possible in 2-dimensional systems, not in 3-dimensional systems. So, in 3-dimensional systems you have only 2 possibilities, fermions or bosons. Okay, so what we are saying now is normally at room temperature, for example, the particles have enough thermal energy and they can occupy higher energy states. Okay. That happens even for fermions and bosons. But in fermions, as I said, that the basic thing is no two particles can be in the same energy state. So, they are filled like all of them cannot be in the lowest energy state, that is what is important, and therefore, you have the concept of this Fermi energy and things like that. That is not the case for bosons. All the bosons can be in the lowest energy state, that is possible. Normally at room temperature that does not happen because of the thermal energy that they have, they can go to higher energy states.
Was half, no?
Huh?
For the case of bosons, the probability was half for being in a
No,
one state. Mean you calculated?
that was the ratio. Ratio was 1 for bosons, and that was for one like typical system of three particles or 3 states and 2 particles. But basically it was more than Fermi Maxwell-Boltzmann, that is what I wanted to point out, and secondly it is 0 for Fermi-Dirac, that is what was important. So, we can have all the bosons in the lowest possible energy state, that is possible. Okay. So, that happens at very low temperatures. So, let us talk about what happens at low temperatures. Okay, one more, maybe before that I would just like to discuss this. One example which I wanted to, when I talked about electron spin, I wanted to discuss this, but I forgot. So, as we said that electrons can be an up spin or down spin, and when that is possible, what we are saying is we are applying a magnetic field in the z direction. Okay. So, correspondingly you have this Pauli matrix which is, and the 2 states corresponding, the 2 eigenstates of this are what we denote by up state and down state. Huh? Yeah. Actually corresponding, what we should have is sigma z. This actually represents the spin. I just wanted to describe one situation which you should tell to the students because it is not really obvious. Therefore, I wanted to discuss this, and this happens because of the measurement.
0 minus 1.
Yeah. So, corresponding eigenvalues are plus and minus 1, and the corresponding eigenvectors are this and this. And as we said that any possible combination the electron can be in any such state which is a superposition of these two. Now, suppose I make a measurement of the z component of spin of the electron. After the measurement, as we have seen earlier, that after the measurement the system collapses into one of the eigenstates. Okay, so, it will collapse either into this or into this depending on the values of alpha and beta, and also at that instant what happens. In general, mod alpha square is the probability of getting this as a result of measurement up spin, and mod beta square is the probability that the result of measurement will give you a minus 1. Similarly, we have sigma x, that is in the x direction. So, 0 1 1 0, and the corresponding eigenvectors, if I denote by x, okay. So, this psi I can write as a column vector alpha beta, assuming that these are the eigenstates. So, I am expanding this in terms of these 2 basis functions. And now I make a measurement, and let us say that after the measurement the system collapses into the up state. So, corresponding state will be this. Now, you make a measurement of x, means what? You are operating by this operator x on that state.
First we have applied sigma z, then sigma z.
Yeah. So, you have applied sigma z on S, which was say 1 0 0 minus 1 alpha beta, and then after measurement it collapsed into one of the eigenstates. So, I have this 1 0. Now, since I am making a measurement of sigma x, I should expand this as a linear combination of these two states. Okay. So, let me say I write this as alpha prime 1 upon root 2 1 1 plus beta prime 1 upon root 2 1 minus 1. Okay. So, this will be 1 upon root 2 alpha prime plus beta prime alpha prime minus beta prime. And now I make a measurement of sigma x. That means I operate on this by sigma x. So, sigma x operating on this state alpha beta, which is now become 1 0 after measurement of x, this will give me sigma is 0 1 minus 1 0 or 1 0 1 0, and this is alpha prime plus beta prime. Okay, whatever you get, you write it as now a linear combination of these two, and after that measurement it will collapse into one of these states. Okay, so let us say it collapses into this, and now you make a measurement of sigma sigma z again. See, so you do not understand, normally the students do not understand, that is what I wanted to point out, is you have made a measurement of sigma z, then you have disturbed the system. If you had made a measurement of sigma z and again you had made a measurement of sigma z, then it would be again in the same state. If it has collapsed into 1 0, it will remain in 1 0 and the measurement result will always be the same. But after that, now you have made a measurement of sigma x. So, it has disturbed the system. Now, it has gone into one of the eigenstates of sigma x, and now again if you make a measurement of z, then you will find out when you do actually these calculations that the probability of both the states is half. So, it can be either in the up state or in the down state. So, that is what I just wanted to point out, that when you disturb the system, you make a measurement, you are going to disturb it, then it will not remain in the original state, which was an eigenstate of sigma z. Huh? Obvious, but normally I do not know whether students really.
The sentence is that whatever measurement you make
Yeah.
of that observable, it will collapse to one of the
Yes, yes, yes. Okay, so that was what I wanted to talk about. Then last is, before we go to Bose-Einstein condensation, I also wanted to show how at large temperatures or low densities the three statistics actually become the same, and then we will talk about Bose-Einstein condensation. Or beta, right. So, if I try to plot the occupancy, occupation number you can say, as a function of this, this is 0 where epsilon s is equal to mu. For Fermi-Dirac, we have seen that the occupation will be either 0 or 1. So, if you try to plot it as a function of this, goes something like that. The Maxwell-Boltzmann distribution goes like this. So, this is Fermi-Dirac, this is Maxwell-Boltzmann, and the boson distribution goes like this. So, when beta is large, so did I do any? Okay, beta t, yes. At high temperatures, this has to be greater than this, otherwise it will become negative. So, this quantity is large. Correspondingly, we define what is called a thermal wavelength. So, at low densities also this thermal wavelength actually is related, and I am not going into all the details, but basically mathematically when I say that this quantity is very large, it is equivalent to saying this is very large, or you can say n upon v into lambda cube is very small. So, if densities are very small or temperatures are very high, then these systems behave almost same. So, the difference between the Fermi-Dirac statistics, Bose-Einstein statistics and the Maxwell-Boltzmann statistics, it becomes at very low densities of particles, they behave almost same. So, this is one thing which I wanted to. Huh? No, no, it is always less than 1. The figure that you had seen, the occupation number was always less than 1. That I do not know, that he can talk about. Entanglement is possible or not possible, that is what he is asking.
See, entanglement we assume particles to be distinguishable, and I mean we have some work done for fermions, but let's not discuss about that. That is complicated.
I can't comment on that. That is what I can say. Okay, so what I was saying about Bose-Einstein.
That you will come across, you can take all particles distinguishable. Don't worry about.
That way you can also look at it. That they start behaving like Maxwell-Boltzmann distributions, so they become distinguishable.
How should I look at it? Whether I should look at that both are all are distinguishable, or should I visualize them as two cannot be in one state, or there are three things, not three different things.
Don't worry about this. These things will not come into the calculation of entanglement or effects of entanglement and all these things.
So, what we say is at very low temperatures, the particles will not have enough energy, the bosons will not have energy to occupy the higher states, excited states, and they would all come into the ground state, and all of them will be occupied, or all of them will be in the lowest possible energy state. That is what we call as the Bose-Einstein condensation. But then this happens only in certain things and not always, not in all systems you see Bose-Einstein condensation. That is one important thing, and actually mathematically I am not going to do that here, but suppose I say that N0 is the probability or occupation of the lowest energy state, and if I say Ne is the occupancy of all the higher excited states. Okay. So, this is the lowest energy state occupation, and this is the occupation of all the higher energy states. Mathematically it can be shown that for a given volume and temperature, the total number of particles that can be here in this higher energy states, that is restricted. And if the total number of particles in your system is less than this, then there is no problem. But the moment the number of particles becomes greater than this, all of them will en masse be forced to go into this state. And that is actually what is Bose-Einstein condensation, that the probability of higher occupancy, states of higher energies is very, very small, and all of them try to come in the ground state. This is not coming down at some position. This occupancy we are talking about in the momentum space. So, although the name condensation is given here, it is, and normally the thing is also like analogy is given that gaseous state you go to the liquid state kind of thing, condensation. So, as the temperature is lower, it goes into, say it becomes liquid, gas becomes liquid. So, condensation is the only word that is common, but otherwise the phenomena are totally different. You are not talking about the occupancy of states in the coordinate space, you are talking about the occupancy of states in the momentum space. And then at that point what happens is the wavelength that I have discussed here, the thermal wavelength, that becomes so large that you cannot distinguish between one particle and the next particle. So, all the atoms in the Bose-Einstein condensate, they behave as if they together form one entity. You cannot distinguish between the particles, and that is something called a super atom or something like that. And the first Bose-Einstein condensation which was shown was for rubidium. And here when we are talking about rubidium, 87 is, so total number of electrons that you have in this atom is odd. So, we expect that the spin should be odd. So, actually there are two things, one is electron spin which is half, and another is the spin of the nucleus, that is 3/2 for this system. So, I am not going to actually calculate or show you how they are calculated, but I just wanted to give a number. I do not know whether I have it or not. Yeah. So, the number of protons in this is 37, number of neutrons is 50, and number of electrons is 37. And there is actually one electron in the last unoccupied S, S shell. So, that gives rise to total spin half for the electronic system, and this gives, and this is actually experimentally also measured, the spin of the nucleus, and therefore, the spin of the atom is I plus j or I minus j. So, it can be 2 or 1. So, therefore, this whole, like this, each atom behaves as a boson, and therefore, you can get a Bose-Einstein condensate which is made up of rubidium atoms, because the spin is integral. And the most important thing is they all behave like they are as if they are all together an entity. You cannot differentiate between one particle and the other. The wave functions of all the corresponding, the wave functions of all these atoms, they start overlapping. So, you can't talk about individual particle. But as I said that this is not an overlap in the real state. The wave function overlap is in the real state, you can say, but these are states in the momentum space. And this is what is at very low temperature you get this Bose-Einstein condensation state. And this is also one thing that is used in quantum computers. So, I will stop here. Most of the things that were expected I have covered, but if you have any difficulties or anything which you have not understood, we can discuss that.